see if they have. They might have.
Audio check, test. Is the signal already coming through? HDMI?
It should be.
Yep, looking fine. Let's see this. We might want to switch laptop when my colleague arrives because, as I found out yesterday, on my PDF presenter console, the videos don't show. On his, they do. Same package version, same Ubuntu version, both Intel graphics chipsets.
So why is that?
I haven't debugged. I don't know. I don't know yet. But let me see if it, maybe with dual screen, let me check. But I think they're not. Oh, and it's slow. It is very slow. So, I think I'll choose the other tool.
Actually, not yet.
But we can use yours if you want.
Testing 1, 2. Check 1. Check 1, 2.
But I don't know why it is not working, and before was not working.
Okay, let's see if this works. Can you hear me? Okay. So good morning, everyone. It's so nice to see so many people here in this kind of stormy weather conditions right now in Vienna. So welcome to this 2024 Linux Security Summit Europe, this time in Vienna. And we have actually quite a lot of registration in person. I guess people will be still coming, and we do have some changes in the agenda because of the weather, so we had to rearrange some talks slightly. You know, some people are getting in late, so don't be surprised if you see some talks flipped over. And like specifically now for beginning of this day, we have the first break is going to be longer, 45 minutes, because we had to kind of adjust to things, so don't be surprised. So so for those of you who don't know, we have Linux Security Summit is a developer conference with the focus on the state-of-art Linux OS security, and we have two events, one is Linux Security Summit North America, which usually happens in around spring, somewhere in US, and this one is the autumn second event, which happens in Europe, also in different places every year. As I said, this time we're here in Vienna. And the focus, as I said, is the development, discussions, collaborations. We always have the time at the end of each day for both sessions. So if you're interested and want to submit topic for both session, please just write it down. We have, as you exit from this from this room, I think right on the left there is a both session board. You can just put the topic you're interested and contact name, so that people know whom to and the time. And this room would be free after the official program when we both starts. This room is free. You can it's not going to be recorded, but you can use places of this room or in the hallway to set up your both. So and I would like to thank everyone who submitted talks for this year Linux Security Summit Europe. We're only 2 days, pretty small conference, so we have pretty a strict review process, trying to accept only submissions which really advance the state of the art in Linux security. So thank you everyone who submitted, and of course people who will be presenting. For those who would be presenting, I have one kind request, that we don't have any microphone for questions going around, so please repeat the question so that everyone in the room can hear what the question is. I mean, that's for speakers. And with that, I think we are ready to move to our first talk, which is going to be given on very interesting topic. I guess many of you remember this emerging supply chain attack due to the backdoor which was planted in executiles. So I think it's made a pretty significant amount of noise in Linux community, and it would be my pleasure to welcome our next speakers to give us update on this. Thank you.
Thank you for the introduction. Welcome everybody to Vienna, even if slightly wet. I hope everybody made it roughly all right and is staying safe out there. Now, my colleague Mario Linz and myself, René Meyerhofer, we are from Johannes Kepler University in Linz, so we are kind of local. Normally it would only have been a 1 hour 15 train ride. Yesterday it took slightly longer by car to get here. But it is our honor, it's our pleasure to have been invited here to talk a little bit about what we have been doing over summer or before summer to try and dig into XZ. Now, you might want to ask why, and why should you care? What is XZ? What are the XZ utils? What is libLZMA? If you haven't really used it explicitly, for example with tar as a compressor, uncompressor, decompressor, you may not have been exposed to XZ before. So why should we care about a kind of small, obscure packer if you're not using it explicitly? Well, there is an open source project, so we are talking about open source here. There's a GitHub repository, there's a GitHub page now. Previously it was hosted somewhere else. And again, if you haven't really used it explicitly, you may not have seen those repositories. And then it came to media attention. Why was that? because xset has a very large reverse dependency tree. You may not have heard of it before, but you have used it implicitly in many different places. If you do a really quick run of what is the reverse dependency tree of those packages, libelsetma5, which is the library implementing the xset compression, decompression, it's here on the top line. You can see that it's in nearly 30,000 packages on current Debian or Ubuntu. That's a lot. So this thing is implicitly or explicitly, so maybe even through transitive dependencies, in a lot of packages. It's pretty much on par of some of the other packer libraries like bset2 or libset standard one, which has seen some more interest after that xset attack came to light. But I was also interested in how does it compare to others. So for example, curl. I mean, there's the saying curl is everywhere, right? Yes, curl is being used in too many shell scripts, but the actual libcurl is only in about 1/3 of all the dependencies that libelsetma is in. Or stuff like SSH or JPEGs. I mean, JPEGs is a complex, kind of complex image format. How often is that used? In about, libcurl is in about 1/10 of all the dependencies, libjpeg in about 1/3 of the packages that libelsetma is in. And how does it compare to other libraries that we use? Well, libc6 is not that far off, quantitatively speaking. So libelsetma is, you could say, pretty much everywhere. Now, why did we start to look at that? Because it is also used indirectly in OpenSSH. Funnily enough, OpenSSH doesn't use it directly in upstream, but some distributions, some Linux distributions patch the OpenSSH source code to use libsystemd, and libsystemd depends on libelsetma, so there you are. Now, why did we actually shine our light on that library? Because somebody, Andres Freund, noticed that his OpenSSH logins on the server side took slightly longer than usually. There was some monitoring in place, and he started digging, and this is where we ended up in. It's not only in SSH, but in stuff like the Linux kernel. I mean, to be fair, this is not the exact same source code. It's what's called xset embedded, but the same unpacking code is also used in the kernel itself and many other packages that you may have heard of that have quite an attack surface in the sense of open network ports or Tor, Firefox, etc. All those packages directly link or indirectly link to libelsetma. So how did we get there? How did we get something into an attack into SSH, one of the probably most closely monitored open source packages out there? It's not easy to slip something in there because many people are looking into what goes into OpenSSH. It wasn't the SSH directly being attacked, but it was the so-called supply chain. And this is the main topic of today's talk, that we tried to identify what were the critical steps in this attack path. We tried to identify what was necessary to pull this attack off, and to round it off towards the end of the talk, what we can actually learn from this part. So just caveat, this is not a talk about the details, about the actual exploit, about the real injected backdoor. There have been other talks in the last month or two that have done a great job on doing that. This is not in our scope. We are trying to generalize. We're going to a more abstract level, trying to learn how this was pulled off from the, you could say, organizational or structural perspective. And for this, we look at 5 different stages. For stage 1, over to my colleague.
Yeah, hello and good morning also from my side. Yeah, and I will start with stage 1, building trust. Imagine you're an open source developer working with passion on your source code, and suddenly on some day your project gets integrated into a widely distributed system like Debian. And that is something that is, I guess that this must feel like there is a lot of responsibility that comes with that if your project gets integrated into such huge systems. And this is something very similar that happens to Lassie Collin. And Lassie Collin was the original and responsible maintainer of the xset project that we are talking today. And one of the first interesting aspects that I would like to start with is that the xset case didn't begin with kind of fancy hacking tools or sophisticated code. It all started with social engineering, a tactic that preys on humans' emotions, trust, and also pressure. And pressure is very important for today's talk that I will slightly highlight within the first building block that we have prepared here. Yeah, and I want to start with the stage 1, building trust, and this is about the social engineering tactics that the attacker used to exploit trust within the open source community, and this is very, very interesting and important, essential for the attacker to be successful in the end. Let's start with the first commit. So we have identified one of the first commit we have detected was by a GitHub user called GRT75. This was not a very specific commit, but we detected that one. The user itself seems very friendly. At the first place, the user seems very friendly, very supportive, a very valuable user actually for the project itself, for the open source project. And later, we find out that the user has other intentions with this open source project. And one thing that maybe is also important for the further presentation slides, this user is named Jiatan, and this username GRT75. The first commit was not very special, but suspicious, I would say. So the user replaced a save fprintf function with an fprintf function. We don't know yet why this was done by this user, but it is kind of suspicious, right? So currently we are not aware if this one is really relevant for the final attack that the user tried to do, but it is a suspicious one, and so we should maybe focus on that. But that was on November 2021. Afterwards, everything started with this patch. So we had a patch via mailing list in April 2022 by this user, Jiatan, the attacker. And there, the social engineering stage actually started. So the first thing, there was another user involved, Jigar Kumar. And this user replied on this patch via mailing list that this is a quality of life feature, and this will unfortunately take years until the community actually gets this. So this is kind of setting up pressure on the original maintainer. Then Jiatan, the attacker, the friendly attacker, the very valuable and supportive attacker, tried to slow down the pressure and so on, makes the statement that the contributors to the projects are hobbyists, so we have to take care about their resources and so on. Maybe we should also talk within this community, within this round, about that topic. So the open source developer doesn't have 40+ hours a week for fast releases and high quality. So this is more a supportive statement to build up trust within this project. Then I've summarized some more statements from different users. So for instance, patches spent years on this mailing list over 1 month and no closer to being merged. Is there any progress on this? Very interesting, the last sentence. Why can't you commit this yourself? And this was the first sign that the goal of the attacker was to get commit permissions on this open source repository. Then, in the meantime, this was in May 2022, there is another patch, thread ongoing, but this was for the project XZ for Java, so a different one, and a new user called Dennis Enns. And this user also started to put more pressure on the original maintainer, even within another project. Then in May 2022, we saw the first signs of being overwhelmed by the original maintainer, by the responsible maintainer, Leslie Collin. He, for instance, stated that he has a lot of unanswered emails at the moment, and obviously he knows that isn't a good thing, right? So these are the first signs of being overwhelmed by a small open source developer with a lot of responsibility, as this project is involved in widely distributed systems. And then we see that Leslie Collin mentioned the first time the attacker user Jiatan. So, and he mentioned that he might play a bigger role in future, and also that Jiatan is very supportive, and he builds up a certain trust relationship to that user. I don't know if they met, I don't think so, but there is at this point, there is a specific trust relation to a user that contributes to the open source project. And the attacker's goal, this was quite clear, the Jigar Kumar also wants to force that there should be a new maintainer for this project. And he also put additional pressure on that progress will not happen, very, very frustrating and so on, until there is a new maintainer. Then we have another pressure. Why wait until the new version to change maintainer? Why delay what your repo needs? So this is just putting more social engineering pressure on the original maintainer. We also see from Dennis Enns, from the other user, that we have seen for XZ for Java, that he mentioned why not pass maintainership. So it's getting clear what the attackers try to do. And finally, also the attackers get what they want. So I'm talking here about attacker with parenthesis S because we are not aware if it is a single user or multiple or a group of users or whatever. But we think that it might be more users because it was a very sophisticated and resource-intensive attack that we have seen here with XZ. And sorry. And finally, the attackers got what they want because Lassie Collin, the original maintainer of the project, mentioned that Jiatan have a bigger role in the future and that he is practically already a co-maintainer of the project. And we have seen the first signs with that. So in the beginning of December 2022, this was very critical time frame. In the beginning, we see here that the user GRT75 authored the commits, but the commits themselves were only committed by lar HZU, that was the original maintainer, Lassie Collin, but never committed directly by the attacker. And if we see the Git history in the end of December, so December the 30th of 2022, we see the first time that the attacker GRT75 committed on himself. And that was the point in time where the attacker were successful. They got the permissions to directly commit to the repository.
Now with that building trust exercise gone, and caveat here, we assume that most of those accounts, all of those accounts probably were really sock puppet user accounts controlled by a well-organized attacker. Who's behind there? There are some suspicions, but as far as we are aware, there's no proof of who really pulled this off. All we can say is that all the elements point to this being a coordinated and very well executed attack, starting with that trust exercise. Now, stage 2. After, through that building trust stage, having succeeded in getting direct commit access to the repository, the attacker started with a few steps that we frame as preparation steps. Preparation because they already are necessary steps for the attack that followed later on. And if you just zoom back a little to the timeline, this was over 2 years ago that this exercise started, so this was a long game for the attackers, that those preparation steps are required critical path steps in the chain that we've identified, but they in themselves are still what we see as deniable. All those steps in the preparation stage could have had some really benign reason behind them and are not directly connected with the actual attack being pulled off, but they are required for the attack to work in the end. So first stage was another open source project. You may have heard of Google's OSS fuzz that tries to find bugs through fuzzing in a quite large number of open source projects. And the first step here in the preparation was for the attacker to change the primary contact role for Google's OSS fuzz to their email address to be able to make some, like you could say, config changes for how Google's OSS fuzz was used to fuzz, to try to find bugs in this XZ in the libl-ZMA. Through that contact change that was being requested and was being approved, because it's kind of a normal thing if there's a maintainer changeover going on that contacts at other projects for this project are being changed. So this was kind of non-suspicious event if looked at it in an isolated way. Second step, another user called Hans Jensen, again we assume this is another sock puppet account of the attacker, is introducing a change to XZ, which is introducing ifunc. ifunc is really a dynamic function resolver method that can be used to dynamically resolve, to dynamically replace basically function calls during the loading stage of some program, of whatever is using that library. And this is in itself also a benign change, even though for a small project with like libLZMA, one could ask, why do you actually have to use ifunc? It just replaced function resolver for some very simplistic use cases where standard C function pointers were used before. And now somebody proposes to introduce this complex, generic, abstract resolver infrastructure into that library. In itself, it's not an attack, but it's required for the additional stages and could already be a bit of a signal that I call introducing code and structural complexity into a project that might make it more likely to be attacked in the future. But again, in itself, completely deniable. This change in its own is not an attack. The code change is very small, as you see, just replacing a function pointer by that ifunc attribute to use that generic resolver infrastructure. And with that, going back to the first preparation step, actually disabling certain fuzzing, specifically the ifunc fuzzing on Google's OSS fuzz for that project, with the reason that this is that recently introduced ifunc change is not compatible with the way that fuzzer works at the moment, so let's disable it. Again, you could argue deniable because it was actually documented at the point that ifunc is compatible with this kind of fuzzing, so yeah, the obvious easy way out is to just disable it. But again, it probably, we don't know that for sure, but it probably helped the attackers not being detected sooner. We are not completely certain about that, so I don't have any signals that Google's OSS fuzz would have detected that injected backdoor otherwise, but again, a slightly suspicious change. But all of that so far deniable. Now, this was because of that contact change before and because of the contributions to the upstream repository by that same user before, this was automatically flagged for ready to merge in the other project in Google's OSS fuzz and was then manually committed to be merged. And now we move away from the deniable stage into the actual attack.
Okay, yeah, in this stage, the inject backdoor stage, we have extracted a brief portion of the attack itself because it's highly sophisticated and has a lot of parts, but we should be kind of a little bit familiar with some of the attack patterns that the attacker really used in that case. And we have prepared one example. We have also prepared one slide with a lot of sources on it, very valuable sources, because a lot of other people already analyzed this attack on different layers of depth towards the machine and the system. And you can look at the details up if you are interested in. So it all started, the injecting stage started with injecting the backdoor by adding hidden, so the backdoor was hidden in test files that has been added to the repository. And we have two important test files here in that particular case. We have the bad-free corrupt LZMA test file, and we have a good large compressed test file. And that actually are binary blobs that they are added to perform certain tests and so on. And in there, the attacker, Jia Tan, on the top you can see the name again, introduced the hidden backdoor. And another change that was quite suspicious and interesting, the attacker added the build to host.m4 file to the gitignore file. That was quite strange because why should the attacker do that? And the reason was because in the build to host.m4 file, this file is used on the build server where the package gets assembled and built to start the configure stage. And this file was added to the gitignore because the attacker doesn't want it to be part of the repository where everybody could have a look on it and could maybe reveal the hidden backdoor in there. And we have just extracted one specific command that have been detected in this build to host.m4 file. And this, in the first place, I would say this looks not suspicious. It looks a little bit weird. It was not written very readable, I guess. I don't know. But it's not suspicious in a way so that I would immediately detect that there is something malicious going on with this line, right? So, and maybe we should just go today through this command and see what the attacker were able to do with that. Let's start with the first variable, the GLAM-config-make variable. This was also defined in this build-to-host.m4 file and includes or started a specific grep command with some specific string and whatever to the source directory. And in the end, I've already also prepared a small test environment where I've simulated the real document hierarchy that was also in the project. And if we run this grep command in this document, we see that the bad free corrupt LZMA directory gets extracted from there. And if we substitute this variable in the command before, we see now a set command calling this bad free corrupt test file, then piping it into another variable that we've called with eval, and we have a third one, the GL prefix variable. So and what is about this strange set command? This looks quite strange. Maybe does anybody know in here what this set command could do? So just from looking at it, what do you think is this set command used for? It's not a very common one, right? Sorry? Stream editor? No. So the R is for reading a file. Maybe this helps you. So set reading from file, and what does it mean with \n? What is the attacker trying to do here? Sorry?
Print the file out and understand.
Yes, exactly. This was the intention, because if you call set with an R, read from file, and file \n doesn't exist, of course. And then what is set doing then? Set is just printing out the output what is part of the file. So actually, I would say that set is a hidden cat command. And if we try that in the console, we should see exactly the same output as we would see if we just use cat. So it was just kind of an obfuscation. So that's not very easy for the users, for the reviewers to detect what the attackers is trying to do here. Okay, then we substitute this strange, weird set command again within our obfuscated whole command, and then we start with the next variable, the glPathMap variable that gets called by eval. And this variable includes kind of a tr command that replaces some dashes with underscores and vice versa. And if we do that again in our test environment, we see that the attacker, so I've just echoed one command, test -123 underscore, and if we pipe it into the tr command, we see that the dashes gets replaced with the underscores and vice versa. And this was used by the attacker to actually uncorrupt the content of the test file, because before it was the bad, free, corrupt, whatever test file, it has to be corrupted by intention, because it was a test file to test if the exact tool is properly handling corrupted files. And with that one, the attacker uncorrupted it so that it makes sense again. So the syntax is properly defined afterwards. The last variable, the third one, we have seen in the command before, is the GL prefix command, and this one echoes the variable glConfig-make that we have seen before in the first place, and pipes it into another set command. In the second line, I've just substituted the variable GLAM-config-make with the original path to this test file, and if we run that in our test environment, that was also quite interesting because the attacker used the file extension of this test file, the xset test file, piped it into the set to extract just the xset that is used as a command before in the complete obfuscated command pattern that you have seen before. And finally, this was the whole command. This was the obfuscated command hidden by the attacker in this build-to-host.m4 file, and that is just cat, so it reads the input, the content of the file, of the test file, it uncorrupts the test file with the tr command, and finally it pipes it into the exec command. And I have to also add something that is not in the slide because it was on a later stage. Afterwards, it gets again piped into a shell and got executed on the build host on the machine, on the package maintainer machine, where the package actually gets assembled and built and distributed afterwards to its users. We have prepared a small illustration about with the remaining steps, just to quickly go through it, but there are a lot of sophisticated and very detailed steps in between, and you can look it up on the sources that I will provide you on the next slide. So we are here on the build to host file. We are in the context of the configure. AutoConf on the build machine has been used in that particular case. This extracts the malicious script that we have seen before from the test file, from the corrupt test file. And this one extracts additional scripts that were hidden in the other test file, that good large compressed test file. This was rather big because the name implies it's a good large test file to test the capability of the exec utils to handle large files. And there the attacker also hides a lot of malicious scripts in there to make this attack happen. And finally, this good large compressed LZMA file also manipulates the make file itself. So now we are in another context, the make context, actually building the library. And there, the bad-free corrupt file got evaluated, or let's say repaired another time, but in a different way. So there are other bit shifting operators, so very sophisticated. And finally, the attacker with the make file manipulated the source code of a C file, the crc64_fast.c file. And that contained a function, crc64 resolve, calling a get CPU ID function. And that one was the part where the ifunc resolver pointed to finally on the victim machine, pointed to the malicious function provided by the attacker. And that was the goal. And finally, the liblzma library contained a malicious object file called liblzma. Here, as promised, we have some sources listed here. We have also read the research, the research work from Russ Cox on the exec script, a very detailed one you can have a look on. I would really recommend that one. Also, really nice to recommend is the speaker deck, the second link. It has been some days ago, I guess, on DEF CON, a talk by the user Frogger. It's also very detailed on the attack paths, and so you might want to have a look on that as well. Stage 4, I briefly make this stage as well. Deployment, this was just about how to get this deployed to the end users, to the victims. And we have compared the releases on the GitHub repository page. If we compare the malicious release, that was, one of them was 5.6.0, the other one was 6.1. But if we compare that one, where the attacker only placed the source code there, to a previous one that wasn't malicious, where the attacker also placed the other tar files in the Git repository, we immediately see that the attacker doesn't want the complete binary to be shipped to the victim. The attacker wants that the source code gets built on the machine. So that was by intention. And that's also interesting because at that point where the attacker is able to compromise the build steps that are executed on a build machine, that's quite critical, because a remote code execution would there be possible as well, right? Because the attacker were able to extract a script, a shell script from a binary blob. That was also a problem, binary blobs there, that got executed on the build machine itself. Maybe also one topic that we would like to discuss afterwards. Afterwards, it was quite easy. We have, again, another sock puppet account, Hans Janssen. Maybe you can remember that from the first stage where we tried to have a look on the social engineering tactics. Hans Janssen started to looking for a sponsor at Debian. And finally, another push from another attacker. We don't know yet, but it has also a Proton mail. So maybe it's all because other sock puppets accounts also use a Proton mail and Gmail, and so they used a mix of email addresses or email providers. And this user also tried to put additional pressure. So again, the social engineering tactics to the maintainer, to the upstream maintainer, that they should really publish this package to the community. Okay, now we are exploitation.
Now, 2 years later, 2 years after the attack was starting to be prepared, the attacker was ready to move into exploitation. That exploitation, that is the final stage after having succeeded in getting that code. Again, just a small reminder, this actually constituted remote code execution to that point on the build environment, on the build hosts. If those were not properly isolated, much more could have gone wrong there. Like, for example, trying to, let's say, exfiltrate the package signing keys or other stuff from the build hosts, if not well isolated on the build infrastructure. That wasn't used in this attack, but it would have been a possibility at that point. Now, what was the attacker doing here? Having succeeded in getting the Trojanized libLZMA into Red Hat and Debian unstable versions, basically, the OpenSSH daemon was in that first exploitation stage, the first target of this complex attack. We have some indication because a second version of that attack script that we walked just through a few choice bits and pieces of that attack script. It's very complicated. It gets executed twice, etc., etc. It has some debugging, it has some hooking methods in there to easily extend what is being added during the build process with additional test files in the future, so it actually had some extensibility built in for other attacks. But the first attack, and we were very lucky to have caught this one at the start, was towards the OpenSSH daemon. As already mentioned before, some distributions, particularly the Debian, Red Hat, Fedora universes, patch OpenSSH to include libsystemd, that includes libLZMA, and through that ifunc dynamic resolving infrastructure, upon loading the OpenSSH daemon, that dynamically replaces a few functions, for example, one of them, the RSA public decrypt. Again, another deep dive could be warranted there. This is a whole other talk on how this attack works that we're not going through here. That's not in scope. Just choice bits when the attacker connects to such an OpenSSH server that loads a Trojanized libLZMA. So remember, the OpenSSH daemon is unmodified. It just loads the modified library. That unmodified OpenSSH daemon is injected a function to, if the client tries to authenticate with an RSA public key, that RSA public key decryption is actually used to inject commands into the OpenSSH server through that function overload, through the generic ifunc resolving function. That gives the attacker capabilities like complete remote code execution on that OpenSSH server, just simply bypassing all the authentication on that system and basically owning that machine if OpenSSH, as it usually does, runs as root. Funnily enough, the attacker even tried for that old nobus, the nobody but us thing, because their commands need to be signed with an add private key that supposedly only the attacker knows, and where the public key was attached within that Trojanized libLZMA. So there was even some authentication of the attacker going on there. But it's still an unauthenticated remote code execution from the point of view of the authentication that the machine actually wants to do there. Now, again, not deep diving into that one, but what you can see in those multiple stages is this was a very complex, very, very well executed attack consisting of multiple stages. We assume that the attackers, probably plural, are really professional in what they do, because as far as we can see so far, they didn't make a single operational mistake in trying to in getting their identity actually revealed. There was one mistake, so the shell scripts that are embedded obfuscated, embedded into those text files. They seemingly had a bug before because there was another upload. They had to fix a bug and fix the test files in the repository to make them actually run. But it was only a single replacement. There were no other mistakes made during that attack that we are aware of. It was really well executed and will be textbook material in our university lectures for years to come. Now, what can we take from that? Those 5 stages, complex attack, really good learning experience, but what can we actually take as takeaways on the generic level? We've tried to come up with 3 parts of the attack chain where we can see some signals, and this is hopefully something for other open source projects to learn from. So look for signals of social engineering. Somebody building time pressure, building social pressure, the fear of not keeping up with changes, etc. This could be a signal for malicious behavior if that pressure is being built up, if that pressure is being kept on. Then signals for what we call bug doors. So bugs that are actually backdoors, but that have some deniability, some obfuscation built into them, where somebody could say that, oh, sorry, honest mistake, but it turns out to be a backdoor, it turns out to be exploitable on intention. What signals do we have for that? I would say any structural or code complexity that is being introduced and maybe unnecessarily being introduced. If there is a patch coming into an open source project that introduces complexity for no immediate gain, please take a double look at that one, because complexity is always the enemy of security, and this was one critical stage in that whole attack path, that introducing the ifunc generic resolver infrastructure was critical, and this was actually not required on the face of it, and it could be a signal. Or also disabling fuzzers, disabling other security mitigations in the continuous integration pipeline could be a signal for malicious behavior. And finally, anything that's hiding or obfuscating is probably a very clear signal for malicious behavior. Unfortunately, one of those that is hardest to detect, because binary blobs in source repositories, we have that all the time for various different reasons. Chipset drivers, some opaque blobs that are required to drive some hardware, some test routines, test vectors for cryptography, for parsing file formats. We have binary blobs all over the place. So these are not in themselves a signal on its own, but weird encodings, dodgy shell manipulation tricks, yes, if you spot them, they are good signals for some malicious behavior going on, but can you spot that line that we saw, that one small deep dive line that we take? Just me looking immediately at that line, if I'm already a small open source project maintainer being overloaded, I probably wouldn't have spotted that. And one person's weird encoding or dodgy manipulation is another person's, hey, this is normal, this is how I typically do things. This is very subjective. So what is hiding, what is obfuscating behavior is subjective. There is no clear metric on how you detect it. So how do we start to look for those signals for other potential malicious behavior in other open source projects? We have a lot of open source projects out there. It's kind of hard to look at all of them. We don't have the person power to do that. So our one call for action that we would like to point the community towards is how do we prioritize? What is major, maybe a major to-do? Which packages do we look at? And we suggest starting to look at other packages of this kind of niche. And what I call niche here is a small open source project with a very large reverse dependency tree. So a very small project being used basically wherever. Plus, additionally, it helps for an attacker if that project deals with parsing complex data formats, because parsing complex data formats, you have some test vectors in there, you have some weird binary blobs in there, you have some parsing logic in C or C++, memory unsafe languages that can probably easily swallow some bug doors that the attacker can use as backdoors to exploit. So if you see that combination in a project, small project, large dependency tree, and dealing with complex data formats, those are, I think, high priority targets at this point to look at and to see if we can see any other malicious signals in there. But this is like the start. This is what I would see as the most high priority ones, because we take the learnings from that case that this is probably nice projects to easily hide attacks in. We have to assume other attacks are going on at this point. We just caught that one. But there are many other projects out there that would be equally well suited for this kind of attack. Now, how can we mitigate? How can we make it not happen in the future? The obvious thing is that if we have identified 5 critical stages, then break any one of those stages and you break the attack, which is true, but if you break one stage, attackers might find another workaround to do the same thing, to try the same thing, but with a slightly different version of how they do it. So as defenders, let's please try to break as many of those stages as we can and make the attacker's life really a lot harder. One thing is, of course, please use memory saver languages, use type safety. This, fair enough, this wouldn't actually have helped a lot in this particular case. It wasn't a C memory safety issue here at all. It was a supply chain attack, but generally it's harder to hide bug doors, to hide something as, sorry, benign mistake, which is then actually a backdoor in a memory safe language than it is in a memory unsafe language, or one with a strong type system. It's also harder to hide those bugs. So let's please do that. But much more important when it comes to those complex stages is to use a safer build system. What do I mean with safer build system? A, reproducibility. Make stuff binary reproducible. If all those build hosts would have taken the same source checkout and reproduced bit for bit exactly the same library independently of the build host being executed on, this would very likely have been caught much earlier. So let's use build systems that are reproducible. Let's also use build systems that are declarative, because quite a number of those attack stages hinged on the fact that you could do willy-nilly whatever arbitrary shell code execution as parts of the various build system stages. During the dependency resolution, during the actual make stage, there were just shell script executions as standard cores in automake, autoconf, in makefiles, etc. If we can get rid of those build systems and make them just declarative of specifying what the dependencies are, what the build arguments are, that attack would just simply break. This attack path wouldn't be possible. So using declarative build systems that are reproducible, that don't have any preprocessor and any side effects. So for example, Rust's cargo without the build RS, so throw away the build RS, then cargo is declarative and kind of safe. That would be a real step forwards for the supply chain security. If you have a continuous integration build chain, GitHub Actions, etc., don't disable fuzzers. Like, make it impossible to disable the security mitigations, make it impossible to disable fuzzers. Of course, we know for a fact that peer review of code commits, that the 4 eyes principle does make a difference. However, for those small projects that have a single maintainer, that's not a realistic option. So if you have got a small project, peer review is probably not going to happen. If you have the capabilities to do so, it does something. So this is really a mitigation against attack. Generally, minimizing code complexity, looking at all your dependency for bigger projects, for security relevant projects, and asking yourself, do you really need all those dependencies? Will do something in this part of attack chain? And a documented, reproducible procedure for creating binary blobs. Funnily enough, one of the commit messages from the attacker introducing those new change test files actually specified that they are now being changed in the repository because they have been created with a reproducible script with a well-set random seed at the attacker's machine, so that those binary blobs are now reproducible. It just turned out the attacker was lying in that commit message, and they never followed up in adding the script that would then create those binary blobs. But the idea is absolutely sound. So if you have some test vectors, if you have some correct or incorrect test vectors, binary blobs in your repository, please create them using a script and commit that script to the repository so that others can see how that binary blob was committed. Binary blobs themselves in open source repositories should ideally go away. There's a pipe dream, it won't happen soon. We have drivers, we have opaque blobs that we need for hardware to run. But as much as we can, please let's remove binary blobs from our repositories. And finally, this is the one where we got lucky. This is, in the post-mortem, we would flag that as what went well. There was some monitoring in place. And that monitoring was the trigger to actually catch that behavior. We should learn from that as well. let's do some more monitoring of runtime behavior of our packages and flag any changes to that runtime behavior. We got lucky one time, but we can use that luck to as a future mitigation. If you can, flag anything that changes from one release to the other. Maybe in contrast to some other suggestions, some other learnings from that case, we actually do not believe that breaking the first stage would be very easy. So something like forcing a real name ID policy or being generally suspicious of any new contributors is, we believe, not in the best interest of most open source projects. So we also, if the assumption is correct that there was some national security service behind this kind of attack and the organizational complexity and professionalism of the attack points towards that, those attackers would actually not have had a hard time in getting a fake real ID that would be in all the right databases and would fool those real name checks. So we believe that this attack would not have been thwarted by real name checks, and we believe that it would actually hurt many of those open source projects. But this is certainly up for debate. And with that, I would just like to point out that there's some more detail than what we could fit in this talk in the archive paper that we uploaded a while ago. And we are very happy to take any questions you may have at this point. Thank you so much for your attention. Yes, please.
I'm not sure if you mentioned it. Did you notice any patterns with the time zone of the emails or the contributions?
So we didn't. We saw that other people did an analysis, a time zone analysis of the... Oh, sorry. The question was, I forgot to repeat. The question was, did we notice any issues with the time zones of commits of the attackers? And yes, this analysis was done. We don't take credit for that. Other people did that. We just read what was analyzed. And yes, there was nice time zone analysis that points to a region in, I would say, slightly east from where we are right now. There's no clear indication, but if we assume the attackers keep to a nice like 8 to 5 working habit and most of those commits actually came from that, then it points to that time zone. But this is just one indication, and attribution is hard. I try not to read too much into that because the professionalism with which those attackers acted could very much mean that they pulled odd hours from where they actually live to point towards that. So the IP addresses fairly consistently came seemingly from Singapore. They used a VPN. The name points to, you could say, Chinese origin. The time zone points to somewhere slightly closer to here at the moment. There are conflicting signals, and this is why we haven't even tried to do any attribution, besides the very strong suspicion, which is backed by multiple signals, that this was a very professionally run operation. Probably not a single person, but a team that is well organized and well practiced in operational security. Yes, please.
Have you thought about some automated methods to analyze maybe Git history or something like that? Do you know whether these tools exist?
So the question is, do we have tools for automated analysis of, let's say, GitHub commits or GitHub source? There are tools, and I mean, fuzzing is one tool that could be used. We don't know if it would have helped there. Are there tools to analyze automatically what the very great open source community has been doing over the last couple of months in pulling out all those bits and pieces of how that attack chain worked? I don't believe so. Are there good tools that would decode those shell scripts for you that would point out that this could be malicious? Not really. This is why one of my or our main takeaways was the build systems have grown too complex. The tooling for analyzing doesn't keep up with the complexity of the build systems that the attackers exploit. So let's make our build systems and maybe our languages easier again so that we can build tools that help us analyze. But I think maybe I misunderstood.
Maybe we could analyze the Git history and then mark any changes or
Oh.
suspicious commits.
Okay.
It's not only report, just the history of commits and the authors, something like that.
So more detail than the question is there...
Malicious behavior.
Yeah, is there tooling to better detect potentially malicious signals in the commit history itself, not so much in the actual what was committed? I'm not aware of any, because I would say between different projects, in my experience, the style that people commit in differs a lot. So
There was only the ready for commit by the GitHub action, right? So
good point.
there was only maybe there was a GitHub action available on a repository that verified, so systematically verified if the pull request owner is really the primary contact or the maintainer of the specific repository, or at least somewhere in a configuration file mentioned, and if this maintainer has previous commits on this open source repository. And if there are some requirements fulfilled, then the automatic verification by the GitHub action showed that this commit is ready for merge. But finally, the merge in this case, in this particular case, was done by a human after verifying. When the system suggests a human that something is ready with a green check mark and everything is fine, I guess there is a small burden that the human then really merges this one. So maybe we could improve that if that one fits to your question, probably.
And,
yeah.
And interestingly enough, that tooling of marking something as ready for merge based on some of the signals in the commit history was actually exploited by the attacker. Because they changed that one signal of making themselves point of contact in the OSS fuzzer and exploited the tooling that that project put into place to help maintainers maybe spot something going on. So I think my final answer is here, no, I don't think we have tooling to help us spot anything potentially malicious in a commit history going on, because projects are so diverse, and even as humans, I don't think, without the getting lucky part of noticing there's something strange going on and then people starting to dig with this suspicion already in mind, I'm not sure anybody would have spotted that on human review. So I'm trying to summarize the question, which was more slightly more involved, as should distributors or the downstream of Linux distributors maybe take more care, do more review before integrating some of those uploads. And I mean, ideally, yes, if you have all the person power to do that, that would be ideal to double check all those changes coming into a distribution. But with the velocity of changes coming in, I don't think it's going to happen. And this was, again, something that was exploited by the attacker for the Debian case, that the normal Debian maintainer, Debian developer, Debian maintainer, who took care of that xset utils lib lzma package, also didn't keep up with the changes, and this is why they pressured somebody else to do what's in Debian terminology called an NMU, a non-maintainer upload. So somebody who is not the upstream maintainer and not the typical Debian maintainer or Debian developer has stepped up to do the upload upon, again, social pressure, not towards the original project, but social pressure towards the Debian developers to do that. With that wording, hey, why do we have a philosophical debate about when NMUs are appropriate and when not. Just do it because we need this bug fix. And pretty soon after that, it was actually done. Somebody uploaded that package. Ideally, yes, we should look at that. But do we have the person power to actually look at all those changes? I don't believe we do. We need better tooling for that. You could also say that we should maybe have better build infrastructure, and this is why I'm pointing to that. I think one of the most effective hammers, one of the most effective mitigations that we have at this point is to improve our build systems. Make our build systems safer in being less complex, being reproducible, and being declarative, not to allow an attacker, not to allow an arbitrary project to do remote code execution on our distributors' build infrastructure would be a nice step forward, I would suggest, and help mitigate those bugs. Now, this is already ongoing. Debian, for example, has had the reproducibility project for a long time, and many of Debian packages are reproducible. Reproducible within Debian. If we can extend that to other distributions, that would also have been caught much earlier. In fact, so another small tidbit in those attacker scripts that we haven't mentioned so far is they actually check at the configure make stage that it is being executed on a Debian or Red Hat style packaging system. It deactivates itself on any other distributions. It didn't activate on Arch or Gentoo or some of the others because it was probably just properly tested for the main server architectures on Debian and Red Hat-ish systems. So the attacker also attacked specifically those distributions. They were aware of those distributions' procedures on how they take uploads and how they ingest source code and attacked specifically that. If we had more reproducibility among different distributions, that would make an attacker's life even harder, a lot harder, I would say.
Yeah, maybe to your comment about the code commit, maybe I could maybe add that writing proper code commits would also help. So I think I saw some of the code commit examples that you had on the slides, but not very well describing what the change was and why it was made.
Yeah.
So oftentimes, at least my experience is that the code commit
Yeah. Yeah.
messages are not very well written
Yeah.
to describe
So
what's going on.
just repeating the comment, better commit messages would help. Would better commit messages definitely help in trying to figure out what's ongoing in a project, and maybe distribution reviewers to take care of what is being changed. If the attacker lies in their commit messages and they actually make sense at face value, like, hey, I'm changing those binary blobs because I'm now creating them reproducibly, then the commit message can also be very misleading. So I fully agree with you. Better commit messages would be nice, and nobody in here likes writing commit messages, me very much included. But it would help in the review process. Fully agreed. Yes, please.
Thank you. Just trying to look at this from a bird's-eye perspective. So I noticed that you mentioned that it's a likely non-solution to add the real name and ID checks. But just from the perspective of for example, the Cyber Resilience Act of the European Union, it becomes more of an issue. How the entire responsibility is delegated, propagated, distributed. Considering this point, just to maybe provide some checks, ID checks for the maintainers, might have helped here.
So about the last point about real name checks, the comment in question is, in light of upcoming regulation, like for example the EU Cyber Resilience Act, don't we have to do that anyways? I hope I'm paraphrasing correctly. Yes, fully agreed. There is some projects, because of regulation, may have to do real name checks anyways. You may have to collect the identities and keep a track record of where changes came from anyways. I mean, if anybody is working on a, let's say, CC, EAL, etc. certified product, then you have to do that anyways. You have to have a track record of every source line where it came from. It makes an attacker's life harder. We still argue that in this particular case, we believe it wouldn't have helped, because those attackers that we suspect being behind this kind of attack, they would have been able to produce real ID documents. As real as anybody who does this real name check for an open source project would be able to verify it. So in this particular case, would it prevent some other attacks? Maybe, probably. It probably wouldn't have helped in this one. So yeah, it's an additional bar. Is it a bar that's worth it? That's an open discussion to have. Yes, please.
Yeah. To wrap up on the final goals of this attack that we described, you put in there that the goal might have been to inject a backdoor. But is there any hint on the damage control side that they have any further goals? I mean, that this is what maybe this was just the first stage of a very long planned attack, I mean, along 10 years or so.
Mm-hmm.
So is there any action on the damage control side possible to take or has been taken in this particular case?
So question here, do we know what would have been the future plans? Where would it have ended up in? Because this is just the first stage that we caught, injecting a backdoor in OpenSSH. What would have been the real goal of the attackers in the end? And I think the only honest answer is we don't know. I mean, having a backdoor into OpenSSH servers in the wild is a very powerful primitive. And it did make it into, I think, some Fedora unstable, and it did make it into Debian unstable before it was actually caught. It was caught very early on. We got extremely lucky in this case, but it did make it into servers. So my only recommendation that I can give here is, if you had a Debian Fedora unstable server being reachable on the SSH port from the open internet anywhere during the time window while this was already in the Debian package, the libelzma5 package in Debian or Fedora, and before it was caught, like, wipe that server. We have no idea what the attacker could have done with that primitive already, with access to those OpenSSH servers as root. Assume that anything on those servers that have been exposed in that time window is compromised, has been leaked. Rotate all the keys that were on there, wipe everything that was on there is the only reasonable answer for that. What would the attacker have done afterwards? No idea. There's only the signal, the suspicion that the complex build injection infrastructure that was set up with those files, that was already prepared for extensibility, for hooking into the future, for adding additional text files, for more additional, you could say, backdoor payloads to be delivered through the libelzma library in the future. To the best of our knowledge, that didn't actually happen. We caught the first attempt using this infrastructure. But did we get aware of any other packages that have been Trojanized with similar techniques? Probably not. We have to assume that this campaign is still ongoing and that we haven't caught the others yet.
Thank you. Well, the goal of my question was to point to air-gap systems that might not be exposed to the internet, and if there was a need that it might initiate something from, behind the internet.
Thank you very much for that additional comment, the add-on pointing to air-gapped systems. I believe that particular attack vector would not have impacted air-gapped OpenSSH servers, because the way that that we know about this attack required the attacker to submit commands with their signature to those infected servers to do something with them. So an air-gapped OpenSSH server would probably have been out of reach of the attacker. However, I'm already concerned that part of this attack stage was already a shell remote code execution on the build host. We believe that this was not used to attack the potentially air-gapped build systems that have the signing keys of the various Linux distributions on them to sign the packages, but it could have. So even an air-gapped build infrastructure that keeps their signing keys away from any internet connectivity, but that has a, let's say, one-way data pipe to ingest updates from the source repositories into the build host, and then another one-way pipe to get the signed build packages onto the wider internet, but that itself is not reachable or not connected, would have fallen in this attack chain if the attacker had used their remote code shell execution capability to exfiltrate something from the build host by, for example, if they are very well aware of how the Debian or Fedora Red Hat build infrastructure works, to try and grab hold of the private signing keys from that air-gapped system and obfuscate, hide it into the libLZMA and therefore exfiltrate the signing key through the package. That would have been perfectly workable in this attack chain. To the best of our knowledge, it hasn't happened, so we believe air-gapped systems were not impacted and are safe for this particular attack chain, and that's all the detail that I'm prepared to say here because I don't know any better. Happy to. Yes, please. Sorry, I acoustically. Oh, NixOS, yes.
Yeah, yeah. It is built on the base of this reproducibility, but it is not getting quite interesting from that. That's from the industry.
Yeah, so the question is NixOS. How do we, does something like NixOS, is that a solution here? We actually use NixOS in our own build infrastructure for our research group, for some of the research projects that we do in Rust, by the way, because we try to do what we preach. We believe Nix has some very favorable properties, and I would consider it nearly a safe build system in those definitions here. It's not perfect yet. We have some nitpicks that we are trying to improve with Nix, particularly when it comes to the hermetic isolation properties and how we build a full trust chain among all the dependencies. So Nix is going quite a far way to integrate the various different build systems and compilers and languages into one build infrastructure that's kind of consistent. If Nix was used to build that attack path that we see here would have broken, or it wouldn't have worked directly on Nix in this case, but it probably could have been adapted to work on Nix in its current form. There are some things that we can improve with Nix in particular that would be quite an improvement, yeah. Okay, and this is the stop signal for us because we've actually moved way into the luckily extended first break. Thank you so much for your attention. Thanks for all those interesting additional remarks and questions, and enjoy the rest of the symposium in Vienna. Thanks a lot. Sorry, break is after the next session. I was wrong.
Sorry, okay. So good morning, everyone, and thank you for your interest in our work. And I'm Keyring Dai, the first year PhD student from the University of Colorado Boulder. And my research focuses on system and software security, as well as the exploitation development. And I'm also a speaker at Decoding USA. And in this project, we as defenders introduce a crucial and unavoidable problem for developing an on-the-fly quarantine on the Linux kernel, and how our protection integrates machine learning into the kernel to address this issue. And I hope our approach will provide you some new insights about protecting the kernel. And let me introduce the team behind this work. Zicheng Wang, who received his PhD degree this year from Nanjing University, and he's the originator of the basic idea. And Tianjin Chen, the PhD student from Arizona State University, provided machine learning-related assistance for this project. And Yueqi Chen, the assistant professor at CU Boulder, specializes in the system and software security. And Hua Wei, the assistant professor at SU, focuses his research on reinforcement learning, data mining, and urban computing. And this presentation will be divided into 5 parts. And in the motivation part, I will describe the problems we faced and review existing solutions and their limitations. And in the second part, I will discuss the challenges we need to overcome. And next, we will dive into the core techniques we used and describe our tool's components in more detail. Then we'll use a video demo to show how our approach works with a CV case. And finally, I will evaluate our tool in a real-world working environment. And our tool and paper are available on the GitHub and archive. So let's start our first part, the motivation. So along the timeline of Linux kernel development, the life cycle of a vulnerability starts off from being introduced through some commits. And later, this vulnerability will be discovered by static analysis and dynamic fuzzing tools, and then reported to developers. And developers analyze the vulnerabilities, diagnose root cause, craft and test their patches, and once the patches pass the testing and being merged into the upstream, they can be deployed in distros. So in this life cycle, there's a risk time window between vulnerability discovery and patch merging. So this time window lasts almost 2 months, during which attackers have enough time to learn about its vulnerability and develop exploits for it. And this risky time window issue is not unique to the Linux kernel, but also applies to many other open source projects. So now the problem is how to remediate the newly discovered vulnerabilities in the test window before the official patches are available. And here I want to talk about a disruptive solution is not acceptable and show you why. So the figure on the top right shows the number of bug reports generated by Sysbot per month. And according to the statistics, we can see that there are on average over 3 bugs reported per day. And on the other hand, existing sandboxing solutions are disruptive because they require rebooting to deploy. This means if we directly deploy them to have a full coverage of protection, we need to reboot the system over 3 times a day, which is unacceptable. Therefore, an on-the-fly solution which can be deployed at runtime is desired. And luckily, some state-of-the-art works do provide the on-the-fly protection. One notable example is PET, which is presented at Usenix Security 23. PET prevents discovered errors from being triggered in the Linux kernel. So given a bug report, it first constructs triggering conditions of this vulnerability offline. At runtime, it checks if the triggering condition is met or not. If the condition is met, it prevents triggering and does exploitation attempts. However, this approach is limited. It prevents triggering only in the specific context manifested in the bug report. So if an attacker changes their method of triggering a bug, like triggering along a different path or a different site, this protection may fail to function. Another work on the fly solution named SEEK is more general. This figure on the top right illustrates a typical memory layout for hit out-of-bound exploitation. So by triggering the out-of-bound exercise introduced by the vulnerable object, attackers can read or write sensitive data in the victim objects. So with this ability, attackers can further escalate privilege. And essentially, the procedure of kernel heap exploitation is to create overlapping between the corruption caused by a vulnerable object and sensitive data in the victim object. Therefore, to thwart exploitation, SEEK isolates vulnerable objects, victim objects, in the different regions. And different types of objects are stored in separate caches. And for objects of the same type, SEEK inserts guard pages and random holes to defend the cross-cache attack. While SEEK is more general than PET, it is also limited. It can be bypassed if the attackers exploit the legacy objects. For example, if certain objects are already in the memory before SEEK's deployment, they can still be targeted and abused by the attackers. And let me explain the legacy objects problem in more detail. So as you can see from the right side of the site, legacy objects are allocated before T0 when the protection is deployed and released after T0. So when the protection deployed, legacy objects are untracked, which means the protection cannot determine the type and the size of legacy objects. So what if a vulnerable object or victim object is a legacy object? These objects are not isolated differently and can be mixed with each other. It's providing attackers with many chances to abuse them. And according to our statistics, over 10,000 objects have lifetime more than 10 seconds, and they are frequently used with an average of 22 modifications during their lifetime. So the main innovation of our work is to audit accesses to the legacy objects, make on-the-fly solution practical. So in the next part, I will introduce the technical challenges we made in auditing legacy objects and our high-level solutions. So recall the legacy objects were allocated before the protection is enabled. It means we cannot place or retrieve KASN-like data for these objects. So as a consequence, when a legacy object is accessed, its basic information needed for auditing, such as the start and end address and its tab, remain untracked and thus unknown. So when we observe an access to these untracked objects, how do we know that this access is illegal or not? So let's use a real-world out-of-bound exercise to illustrate this in more detail. The C statement on top right side accesses the memory via a pointer plus offset. And the base pointer is watch filter, type filter, and the offset is Q-type. And its corresponding instruction BTIs first test and then sets the bit in the target memory. And in this instruction, the base pointer is register R15, and the offset is register REX. So at runtime, the accessed address is R15 plus REX. And how do we know it's not exceeding the boundary? So our solution is using machine learning to help us infer the type and access of the accessed object and match it with the ground truth. If they mismatch, which means the access is illegal. And as human beings, the content stored in the memory are not biased to us. However, for machine learning models, these data are the feature of different types of objects, which can be used for inference. So to the specific example, the machine learning can tell us the type of the accessed object is a message, And type message is different from the ground truth watch filter. Therefore, an illegal memory access is detected. And the second challenge is how to ensure the integrity of auditing. The Linux kernel, machine learning model, and the vulnerable components all share the kernel space memory by default, and they all have the highest privilege. This means vulnerable components has the opportunity to tamper with the machine learning model's data, then bypass the protection and compromise the entire kernel. So to solve this challenge, we audit its read and write operations launched from the vulnerable components to make sure it does not violate our security policy. For example, the kernel can read and write data in the vulnerable component, but the vulnerable component can only read from the kernel. According to our investigation, only using memory read is nearly impossible to compromise the entire kernel. So we audit subject switch to make sure malicious value from vulnerable component will not be passed to the kernel through function call or return value. And we achieve auditing through kernel code instrumentation, and further create a private hidden stack to quarantine vulnerable components data from the kernel data. So in this part, I will introduce the eBPF and the machine learning technique backgrounds, and then go through each component of our approach. So first, eBPF is an ideal infrastructure to implement kernel-on-the-fly quarantine. It works like at a sandbox virtual machine in the kernel. Its feature enables developers to extend the functionality of the kernel without modifying kernel code or loading extra modules. eBPF is an ecosystem that this kernel has the ability to hook instructions, kernel events, syscalls, and network packet. It's very static and dynamic analysis to guarantee eBPF programs will not break through the sandbox. And the just-in-time compiler converts the eBPF instructions to machine code, improving the runtime efficiency. And eBPF maps provides like hash map, array, ring buffer, and other data structures usage. And its helper functions can interact with other kernel subsystems, help eBPF call some kernel functions, or read and write kernel data. And we compare the three modules which are potentially be suitable for our task: the decision tree, random forest, and deep learning. The decision tree is used for both classification and regression tasks. The goal is to create a module that predicts the value of a target variable by learning simple decision rules inferred from the data features. And a random forest is an example of decision trees designed to improve the robustness and accuracy of predictions and anti-overfitting. So for deep learning, the model is more complex than the two mentioned modules. It uses artificial neural networks to perform sophisticated computations on large amounts of data. And the structure includes many layers, and the training process includes the input data and the forward propagation, the loss calculation, and the backward propagation, iteration, and so on. It has a powerful ability of learning and extracting features from complex data. And this figure shows the overview of our approach. T0 represents the dividing point between the preparation work and the completion of the deployment. So first, the component is object profiler. It uses its own eBPF program to collect object data for machine learning model training and gathers type and other information for later auditing. And the machine learning model is trained based on data collected by the object profiler offline, then provides the module for the eBPF program's inference. The code analyzer analyzes the kernel binary and the source code to identify instruction entries for instrumentation. And eBPF programs, it is responsible for code instrumentation, type inference, vulnerable component quarantine. So after these steps, our tool is successfully deployed, effectively constraining the vulnerable parts from compromising the whole kernel. So let's enter the first component, the object profiler. The goal of the object profiler is to collect and filter data for later machine learning model training. So how to retrieve data? We use an eBPF program running in the kernel to hook object allocation and its release sites. So at the allocation site, the stack trace of the allocation and the address of the object are fetched and stored into the eBPF maps. And we use that caller, a fuzzing tool, to diverse execution context and enrich our data source. And what content and when should we collect data is essential to the accuracy of the machine learning model. As mentioned earlier, an object may be referenced many times during its life cycle, so we collect each object's data for training at its release site, because this is it when it possesses the most features that best reflect its characteristics. So for example, most objects are initialized with 0 at first, but just before its release site, they may contain unique values, the memory layouts, and other features can help us to distinguish them from other objects. And we use the object data content as the feature and its type and whether belongs to the kernel as the label. So for the machine learning model, we choose the decision tree model for the following reasons. So first, the decision trees performs better on the tabular data compared to the deep learning modules. And they are interpretable. And once the model is trained, it has a fixed depth. This ensures that the execution time will not exceed a fixed value, which is crucial for this kernel's runtime efficiency. And since we are using integers as features, the decision tree model can run down its threshold, maintaining the quantitative accuracy. Compared with the random forest, the decision tree model can be relatively easy to be converted to a BPF implementation. And the colon analyzer component is responsible for identifying which instruction should be instrumented. And the procedure on the top right shows, so first we use an open source binary analysis tool called Keyring to analyze this kernel binary file, VM Linux. And our rules are shown on the left. It specifies instruction types like the indirect jump, indirect call, memory write, and subject switch. So considering the performance impact is tied to the number of instrumented instructions, so we have done the following optimization. We skip read instructions, determining address, and redundant check. Determining address is easy to understand as the attackers cannot control the address they want to write. So the instruction type is useless to them. And the redundant check means if there are many memory access instructions use the same base pointer, usually it is an array access or multi-fuse access in a structure. So we consolidate multiple access checks into a single check, which means the eBPF programs examines the minimum and the maximum offsets, representing the two extremities. And these optimization methods helped us to reduce the instrumentation entries by 24%. And the eBPF program component plays the most crucial role in our entire approach. In addition to handling all the instrumentation checks, we added extra hyperfunctions to implement the quarantine mechanism. These functions provide capabilities such as setting registers and maintaining private data structures like private heap and stack. And they are for the quarantine zone, and which are not available in the default eBPF helper functions. And to improve the interaction with data structures stored in the eBPF maps, we also designed the corresponding helper functions for quarantine data maintenance. And this allows for more efficient and secure management of quarantined data. So after knowing the specific techniques of our implementation, I will use the CVE 2022-0995 as an example to demonstrate how our approach effectively stops the exploits. So let's start with a simple figure illustrating the root cause and the impact of this vulnerability. This vulnerability exists in the Linux WatchQ subsystem and in the function WatchQ set filter. So by crafting a malicious value, an attacker can control a write range from 0 to hex 80 bytes, which can be larger than the watch filter size, hex 60 bytes, leading to a typical out-of-bound write. And heap function for the exploit is shown in the figure. The attacker first breaks many primary and secondary message structures, and then allocates the vulnerable watch filter object among them. So the out-of-bound write can then make the next pointer in the message struct large enough to point to another secondary message, resulting in a message used up for free. So in this example, a simple out-of-bound write could lead to a UAF and further exploit ability escalation. Our approach can prevent it when the out-of-bound write happens at the very beginning. Let's see more details. So first, the program counter is in the quarantine zone and is trying to access the legacy objects outside the private heap. So if without the machine learning model, the address region and the type of these objects will be unknown to the protection. But with our machine learning model, when the out-of-bound write access occurs, with the address exceeding the end address of the watch filter and locating in the untracked memory, the machine learning model helps infer the type of object as message, which belongs to the kernel. So according to our policy, eBPF program's implemented instruction should access watch filter by the code analyzer and object profiler. But the message is different from watch filter. So this is indicating an error. And let me use two short videos to show how our tools work. So the first video shows exploit without our protection, and the second one shows the exploit stopped by our protection. I ported this vulnerability to the Linux kernel version, which our tool runs on. So then the exploit runs until gets overlapping between 2-second message by out-of-bound write. And in this demo, the primary message with the ID 8174 also points to the secondary message 8179. It's to reference to the 8179 and further use the R for free. And we are still in the same environment and run exploits. So this time I launch our tool before the out-of-bound write happens to simulate the scenario. The victim objects and the vulnerable objects are as legacy objects, and they are out of the private heap and mixed with each other in the untracked memory. So then we can see the exploit fails to create overlapping, and our tool printed the accessed object address. And here comes the final part of the presentation, the evaluation of the machine model's accuracy and the performance of our tool in a practical environment. And we use LM-bench as the micro benchmark and use Phoronix test suites to test common applications as a macro benchmark. And we can see the overhead is negligible no matter whether the machine learning auditing is enabled or not. And to compare to the state of our work, HAKC, which is a sandbox solution, AutoQ also quarantined the IPv6 module and tested the impact of Apache Bench IPv6 file transfer on the performance of the quarantined component. And from the left to the right, each legend means we quarantine a single file, and we quarantine with machine learning, and we quarantine a module, a quarantine module with machine learning. And the final part is deployed HAKC. So in comparison, the HAKC, represented by the green color, showed less overhead for large files. This is because HAKC leverages hardware features to reduce inspection overhead when many memory access are in the same region. However, HAKC cannot be deployed in real time, which is the primary goal of our work. And as mentioned before, there are two levels of granularity of our training objectives. The first one is fine-grained, the specific type of the data object, and the coarse-grained, whether the current data object belongs to the quarantine zone or the kernel. And the coarse-grained, whether the current data object belongs to the quarantine zone, shows the high accuracy. And both decision tree and random forest modules achieve relatively high accuracy, but the decision tree model is more suitable for implementation via eBPF. So therefore, we ultimately choose the coarse-grained decision tree. And here are the details of the parameter tuning for the decision tree. With the feature length of 64, we achieve good results, and the optimal performance is observed at a maximum depth of 14. So using the decision tree, we further fine-tune its hyperparameters. And here's our takeaway. Our work reviewed the legacy object problem, which is critical to the protecting kernel on the fly before patches are available. And we demonstrate how embedding machine learning into the kernel can effectively resolve the legacy object problem. And our limitation is machine model accuracy is not 100%. Our approach can only sufficient as a temporary remediation before patches are available. So for our future work is to mature the prototype implementation and solution to the current cases in the machine learning model. And we are exploiting collaboration and reduce overhead using PLS and hardware features. So thank you for your attention and interest in our work today, and I'm honored to be here to hope you enjoyed it. So if you have any questions or feedback, I'm really happy to hear them from the social media. Thank you. Question. Any questions? No questions.
what you can see in front of you.
Anyway, we'll have the time once Carol
When they on your when you come in Carol against the wouldn't they say that you relate some type of foreign person? Like you said you're like a foreign. So wouldn't they fairly safe when they bring you up on?
So you're not. I guess we're not using this term, right?
Yeah. Yeah, you think that would kind of half, but probably fairly trustworthy. I think that should be good for you that as much. Yeah. Yeah, because you get fast tracks on it. Yeah, I can always illustrate.
All right. I got a green signal from somewhere back there, so I think we're ready to go. So welcome everyone. I'll be talking about confidential computing on RISC-V. So unfortunately Atish couldn't make it here. He's one of our teammates who's working with us on this topic. This topic obviously has a lot of collaborators from the RISC-V task groups. I have a long list of people in the back, so you probably recognize some of those names. So my name is Ravi Sahita. I work at ReverseSync. It's a smaller startup working on RISC-V to bring it into the sort of the high performance data center space. And this is one of the security areas. I also I'm the vice chair of the RISC-V security horizontal committee. If you're familiar with how the committees are sort of formed or created in RISC-V, there's a bunch of horizontal committees working on different areas, and there's a bunch of task groups that are spun off to work on different problems and write the actual specs that the community ratifies. So I'll give you sort of a big picture of like where things are going in RISC-V from a general security perspective, but we'll dive more deeply into the confidential computing aspects of it, and hopefully give you a good picture of that as well. The other key goal here is to sort of introduce this topic, what's going on in the RISC-V space, and also encourage collaboration. Since a lot of the RISC-V work is by definition open source and sort of open domain, right? So those are the three areas we'll cover, and then hopefully we'll leave some time over for questions. So folks are probably familiar with it, but I think it makes sense to kind of start here, like describe what RISC-V is and how the different standards are being created. So as folks probably know, it's an open royalty-free instruction set architecture. It's a very simple spec. If people have looked at it, there's a stable base spec that covers the privilege ISA, and there's a separate unpriv spec that covers the user mode ISA. And there's a bunch of extensions people have been working on over the years, some that have been ratified, some that are in the progress of being ratified. And as the ratification process goes in RISC-V, it's all managed through this RISC-V International, which is a non-profit home, where the stakeholder community sort of comes together, in the form of like the horizontal committees that I mentioned, or the special interest groups, which look at specific areas, and it's like, okay. Like, for example, confidential computing, it started off in the trusted computing special interest group, and then people figured out like, oh, we need these ISA parts, let's go form a task group to work on it. And we need these non-ISA software or hardware parts, let's go form a task group and go work on it. So that's kind of how things are organized. This is a busy chart, but I won't dive into pretty much any of these topics, but wanted to give you like a big picture of like how the RISC-V horizontal committee is thinking about different security topics, right? The big opportunity obviously we have with RISC-V is because of the clean slate design model and the open ISA model. It gives us a really nice place to bring in some of the learnings from various architectures in the past. Like obviously, this is not the first run around at a lot of these topics, but RISC-V gives us a good place where we can sort of cleanly approach some of these topics and put the best foot forward in terms of an open ISA. Like I said, the security HC is looking at various different aspects of it, and they're sort of split between what I call foundational security. That covers also the cryptographic ISA aspects. And there's a bunch of experts there like Marku from PQ Shield and who's also teaching, and Richard Newell and others who lead those task groups, right? So if people are interested, they should look at that. On the software hardening side, there's a lot of work going on in trusted computing. I'll cover some of the confidential computing aspects today, but also control flow integrity. A lot of learnings that have been applied there. Memory safety has recently become an interesting area of, where a lot of people are coming together and trying to figure out what needs to be done there. And there's a bunch of like other what RISC-V calls non-ISA, but also fall in the security space. Like, hey, what should we do for platform hardening? Well, we obviously need things like the IOMMU to be defined, and that was recently ratified, right? So those things are also sort of happening. There's a special interest group that's looking at side channel leakage and trying to understand, okay, from an ISA perspective, what's needed there. Obviously, RISC-V talks a lot about ISA and not as much about microarchitecture. So that's a little bit harder topic to discuss there. But nevertheless, there is a lot of work going on in that space as well. And then I mentioned other things which are sort of not discussed as much in RISC-V International because it doesn't concern the ISA, like the hardware root of trust. But we do have a security model spec that's been recently written and shared with the community, where a lot of those ideas and best practices are trying to come together so that we have one place where practitioners can go and look at, like, give me one place where I can understand what are the different ISA isolation models in RISC-V, like, and how would I use it in the context of a particular use case, whether I'm trying to build a secure service engine on my platform or I'm trying to do something more complete, like confidential computing for a data center like application, right? What building blocks do I need? How do I use them? How do they come together? Right. So that's all going into this security model spec, and that will cover some of the platform lifecycle and other things that are beyond the ISA as such. So as the asterisk or the star shows, I'll dive a little bit to give you sort of a deeper dive into the confidential computing aspects, but there are other topics there for people who are interested in other areas that you can definitely dive into. So quick introduction to confidential computing. I saw Mike somewhere in the audience. He's at the back. So he's the director of the Confidential Computing Consortium. So if you guys have other questions, he's here as well to ask. But let me ask for a quick poll. Like, how many people are familiar with the term confidential computing? Okay, that's about a little bit more than half, which is very encouraging. So I don't have to go into a lot of the background stuff. I can just sort of like deep dive into some of the RISC-V specific stuff. So, but just a quick introduction, right? So, confidential computing really focuses on data in use protection, right? It really observes that a lot of focus up till now has been on protecting how data is stored in a protected way through using cryptographic mechanisms. We've been using HTTPS, SSL for a while now, and it's sort of very pervasive. But the data in use parts are really ignored, and those end up creating a lot of problems, obviously, in terms of whether it's data breaches, insider attacks, general issues with some of like even the build system stuff we were talking about in the morning, like knowing exactly what is running on a platform in terms of its TCP, and being able to articulate that so that you can make a decision about when you want to give data to that system is really the type of problem that confidential computing is trying to solve, right? And that's. So there are critical aspects for confidential computing to come together, right? The official definition from the CCC is performing computation in a hardware-based attested trusted execution environment. So that's a lot of different aspects that need to come together to form the notion of trusted execution environment that has hardware-based protections, that is also attested through some right cryptographic mechanisms, right? So we'll dive a little bit deeper into that and see, okay, how do we break it down from a RISC-V perspective into what ISA capabilities do we think that make sense as a community, and then what other non-ISA capabilities do we need, both in terms of software and other platform elements, right? It also makes sense to kind of look at an example use case, and we were recently, in summer, there was a confidential computing consortium conference where there's a lot of discussion about confidential AI. So I picked that up as one of the use case because it sort of really brings together this notion of why is protecting data in use really critical, right? And confidential AI obviously is there's a lot of discussions about it right now, and it's a good case in point to consider, right? So for that particular use case, right, the idea behind protecting data in use becomes very critical. Like for any of these AI use cases, knowing how the data that you're using for training and how you're generating model weights from that is super critical to protecting not just the model that's being generated, but also the data and how it gets used to do the training, right? So providing confidentiality for model weights, most of the times the training data is proprietary, and also protecting the privacy of who's using the model and how they're using it. How do you make sure the queries you're making to the model are private themselves, right? So a lot of the privacy preserving machine learning capabilities can actually leverage confidential computing as the underpinning infrastructure, right? As I said, putting like data use controls is useful from a variety of different aspects, not just providing insider threat controls of like, okay, who's actually using the data, what information did they generate from the data, how is the derived information being used, and also protecting against general, remote exploits causing sensitive data breaches, things like that, right? So just from a data privacy perspective, it's a good way to quantify exactly who did you give your data to, and what were your sort of properties and principles you were placing around the use of that data, right? So when we break it down further, that trusted execution environment, what does trust in that execution environment means? It actually means that when you're giving data to that trusted execution environment, you want the ability, at a minimalistic way, you need some data confidentiality and integrity, right? Of, okay, who's able to modify the data, who's able to access the data. You also need code integrity for the transforms that you're doing on the data to know that you actually perform the computations that you expected to perform. And also attestation to know both a priori before you give the data over to a certain entity or computing element, and also after that it was actually transformed the way you expected it to be transformed, right? So that's the sort of the process for attestation. It also makes sense to quickly look at this threat model. Again, we could have like a 2-hour-long presentation or more just on the threat model itself, because it's such a vast topic, but it's a good reference point to quickly look at some of these attacks. Right? So when looking at a threat model for confidential compute, or anyone for that matter, it makes sense to look at it from the assets perspective. Obviously for a confidential computing case, the assets are whatever your data is, right? Whatever you define as a sensitive data as a data owner, right? And that relies on a TCP or a trusted computing base, which would be formed with hardware or software, right? Again, that you define saying, hey, my TCP is this hardware engine, this firmware capability on it, this other OS that I'm using, and this particular application or container that I want to run, right? And nothing else, right? You really want to be able to quantify that. And so in terms of attacks, you really have to look at set of attacks or a family of attacks when you're thinking about that scenario, all the way going from simple software attacks, which may be unpriv adversary or privileged adversary, all the way down to software supply chain attacks or hardware supply chain attacks. Right? And we saw a good evidence of the talk today morning in Renee's and in the university talk on some of these supply chain attacks. But there are also other physical attacks and hardware supply chain attacks that you need to be aware of. The other two cases that I mentioned here are cryptographic attacks and protocol attacks. It's not sufficient to basically say, okay, I have ensured correct supply chain in both in software and hardware. I also want to make sure I'm using the right protocols. So the key strengths you're using are not weak, so that you don't run into any of those attacks where somebody can trivially do an adversary in the middle and cause a attack. So those are all important ones to kind of look at as we look at these scenarios. And the one learning as we put this RISC-V, the security model together, was from the community that there's no one size fits all here. We really have to look at these types of attacks, and depending on the capability or solution you're putting together, you really have to make an advised, sort of educated decision on what attacks are within your scope vis-a-vis your adversary model, and which ones are you going to tackle and how, right? Because that's really the cost-benefit trade-off you have to make. In the case of confidential computing itself, some cases might be considered as out of scope. Again, it depends on the capability or the solution you're putting together. But some examples might be very advanced physical attacks where somebody is taking a chip and delayering it and spending months on trying to attack it. Again, that may be in the scope of your adversary model, and then you should address it. Advanced supply chain attacks, right, beyond simple attacks where you have insider threats from your designers, things like that. And denial of service, right? Denial of service from a confidential computing perspective is out of scope, right? Because there the focus is really on protecting the data and making sure that data is never leaked or loses confidentiality. Whereas in some other environments like embedded platforms, denial of service may truly be in scope, right? But that's out of scope from a confidential computing perspective. Okay, so shifting gears a little bit, starting to dive into, for RISC-V, what does it mean, right? How do we achieve these different aspects that we want of data confidentiality, integrity, which can be achieved through access control mechanisms, through cryptographic mechanisms, or a combination of those, right? So we split them into sort of like what belongs in ISA extensions, how do we want to change the RISC-V ISA from where it is right now, what's stable and ratified, to what extensions do we add in the future? What are the non-ISA extensions do we need in this platform, or at least we want to make recommendations on, right, that people may want to think about? And RISC-V sort of has this terminology for non-ISA, which is anything that has not the ISA, right? And that really falls into hardware and software. So whatever work we do in terms of, or specifications we build in terms of software ABIs are also sort of categorized as non-ISA. And in the case of confidential computing, these are really interfaces that we want to build following a lot of the good work that has been done in the community already for Linux, for other architectures like x86, for TDX, for example, or for ARM CCA, and really following a lot of those design patterns to make sure we can align well with some of those interfaces, but bridge the gap to what we need for RISC-V, right? So we'll touch upon that sort of third pillar as well. So let me just keep a track of time. So we'll do like I'll go fast through some of the basic intro stuff because I assume people are sort of familiar with it, but I think it makes sense to touch upon some of those before we dive into why we are proposing some of the ISA extensions, right? So here's a quick background into the priv ISA for RISC-V, and I'll talk about the hypervisor extension as well, right? So RISC-V has basically, like many other architectures, has different privilege modes of operation. There's a user mode for user mode applications, a kernel or supervisor mode, which Linux and other environments see, and there's a firmware or platform mode like called machine mode, right, where usually platform firmware will run. And then there are very simple sort of call mechanisms and trap mechanisms, return mechanisms defined to be able to traverse from or transition from like a U mode into the kernel mode or kernel mode into machine mode to invoke platform services, and the reverse, right? So it's a very straightforward sort of mechanism. This same mechanism is also extended through an extension in the ISA that's now been ratified called hypervisor extension, right? Which basically extends the supervisor mode so that you can essentially support the notion of running, unmodified guest operating systems, right? And when that happens, essentially that's managed in the architecture through this virtualization mode. When virtualization mode is enabled, you essentially have a VS and a VU mode, right? Where your guest operating system and applications can run, right? The idea here is that the hardware handles this notion of when your virtualization bit is active, that your unmodified operating system, when it's interacting with S mode CSRs, it essentially has a bank of virtual CSRs that the hardware will redirect those accesses to, right, to allow the operating system to essentially run as unmodified, right? So this baseline contract of the ISA has been ratified. It's part of the ratified ISA for RISC-V, and we are sort of building on top of that for our mechanisms that we use in confidential computing, right? So hence what we're calling our ISA for confidential computing is called CO, right? It also is a synonym with sort of a protected area, right? But it stands for confidential VM extension, right? So we're leveraging the priv ISA and we're leveraging the hypervisor extension to essentially create this notion of a new entity called a TEVM, or a trusted virtual machine, right? Now, what we observed was having the priv ISA and the hypervisor extension is not sufficient for us to, provide the entire notion of a TEVM, because we also wanted to reduce the TCP and really be able to quantify and allow people to really restrict the TCP that they're running on the platform, right? And this is showing sort of a reference architecture picture for Cove, where we introduced the notion of a TE security manager or a TSM that essentially can leverage the full power of the priv ISA, right? So, you can run it in 32-bit mode or 64-bit mode, RV64, but it gives us the ability to sort of use that same priv ISA without introducing new semantics and things like that, but in a trusted manner, right? And that requires some additional extensions to be able to isolate it and provide certain guarantees that we need in the architecture to build some of those primitives that we wanted of data confidentiality and access control, right? So that's sort of one aspect, right? So we need a capability so that we can host things like a TE security manager. The other thing was we did not want to restrict this to like one TE security manager, because again, thinking about it from different use cases, people may want the ability to run their own attested TE security managers for different use cases, right? So even though I'm in this sort of canonical reference architecture showing two sort of domains running here, where you have like a hosting domain and a confidential domain, the ISA that we are proposing in what is called a supervisor domains architecture allows that ISA to extend to other parallel sort of supervisor domains as well, right? The other important aspect to note here is that once we have that capability of running these isolated domains, we can again leverage a lot of the parts of the priv ISA in terms of the hypervisor extension to allow these TE security managers to further isolate the guests or TVM contexts that run on top of it, right? So that gives us a clear delineation of the security properties, where the root domain manager that you see at the bottom running in M mode has the properties to isolate between what we call supervisor domains, right? And you may have many or more than two. And then each supervisor domain context uses the priv ISA to provide isolation for contexts that are assigned to that supervisor domain, right? And it's really a matter of TCB and choice and attestation policy to decide what workload gets placed in what supervisor domain, right? And you can make a decision about that based on the attestation that you pass to a relying party. There are other platform elements that come into play here as well, right? How do we protect the data that leaves the SOC package, for example? How do we restrict other ISA mechanisms that are active and defined on the platform, like performance monitoring, QoS, RAS, things like that? And other aspects which are important from a device perspective, like debug, right, tracing, those kind of aspects. So I'll touch upon those as well. Lastly, in this picture, as you see, I'm sort of showing these IOMMUs at the bottom, and I'm not showing any devices, but that's something we've been thinking about it from the beginning, like how do we make sure when we host these TE workloads, even though we are leveraging the priv ISA and the hypervisor extension with some additional ISA mechanisms, we want to make sure this works well for wherever the workload runs, right? Whether it's running on a CPU complex or a GPU complex or using functions from an accelerator, the workloads that span those functions should be encompassed as part of the TVM, right? So I'll touch upon some of that we are sort of calling a co-IO extension, which is an important aspect going forward, especially for applications like machine learning. So here's a sort of a 50,000-foot view of the priv ISA extension called supervisor domains. And I'll break it down into some of the separate sort of modular sub-extensions that form part of this. As you know, in RISC-V, a lot of the extensions are built as smaller extensions, and that allows for modularity and choice in terms of when people are implementing things, that they can choose to implement the extensions that they want to implement. So it's supervisor domains, as I mentioned, we want to sort of maintain the priv ISA contract that we have today, but sort of provide this horizontal isolation between these contexts, right? So that platform providers or service providers that are building systems can essentially decide how they carve up the platform and create the TCB sort of pools that they want to create, right? And you should be able to attest to all of these verticals that are shown here, right? So the first primitive we needed in this picture was to provide a way to do scalable physical memory isolation. So for folks who are familiar with RISC-V, know that we've had things like PMPs or physical memory protection registers for a while. There's also IOPMP capability, but those are very limited and targeted towards embedded platforms where you have very static policies of how the memory is carved up. With the supervisor domain model, we wanted a much more scalable model. So I'll jump to that one and I'll come back by one slide. So the first sort of extension we started off was to look at this memory tracking table, right? And so RISC-V has this like weird nomenclature for naming extensions. So when you see something like a SMMTT, it stands for a supervisor mode extension that's applied to machine mode, which is the M in the middle, and then the MTT is the actual feature. So you'll see like this nomenclature sort of repeated for other ISA extensions as well. So SMMTT is essentially a memory tracking table extension that allows the controlling software, in this case the root domain security manager, to essentially assign physical memory access permissions on a page-based level to different supervisor domains, right? So assume you securely booted into a platform, you use the hardware root of trust to measure your RDSM, which is sort of the controlling entity, and then the RDSM can start imposing memory tracking table policies to basically say, hey, here's how I'm carving out my access control permissions across a hosting domain, a confidential domain, and so on and so forth, right? And the ABI sort of works on top of that to define models of how do you move memory scalably between supervisor domains, right? So assume all memory starts off in a hosting domain first, and then is converted to or passed on to a particular supervising domain, and that's all sort of provided by the ABI. And then the ABI is supported through ISA mechanisms to essentially allow for the right memory fencing operations and all those things to happen so that the right permissions are enforced even when the system is running, right? So this picture is sort of showing the logical view of MTT, right? Both from the CPU side access perspective and the IO side access perspective. Like I said, this is from the RISC-V perspective, we were sort of trying to look at this from both the CPU and the GPU side together, right? So that we are not sort of creating some like weird semantics or different semantics between the two, right? So on the CPU side, as you can see, your access comes in through a address. It may be a virtual address or it may be a physical address depending on what modes are activated on that particular CPU, right? But let's take the most complex case of a guest virtual address comes in, right, from a guest context, right? That's typically translated through a first stage page table address translation that's owned by the guest operating system. It's translated by a G-state page table, which is how a hypervisor or the TSM in the context of Cove partitions guest physical addresses, right? Or remaps guest physical address to the real system physical address. And the system physical address is the one that's subject to the memory tracking table lookup, right? So the memory tracking table essentially allows to the RDSM to make a decision whether a particular physical memory resource is accessible to that supervisor domain or not, right? And that basic construct is very powerful in terms of access controlling regular DRAM memory, memory mapped IO regions, or other aspects like interrupt files that live in memory and things like that, right? So we'll see how it's used in various other places. And the same kind of mechanism sort of happens from a device function side, right? From a device side, you will typically start off with, again, let's take a complex case of starting off with a IO virtual address, right, where the device is accessing some virtual address from the IO perspective. And the IOMMU extension for RISC-V, for folks who may not have seen it, was very recently ratified, right? And it sort of follows the same model, right, where you take a particular device request, depending on the fabric the request is coming in from. Let's say for PCI example, it might be a requester ID or a bus device function, and that will be mapped through a device context table to identify the second stage paging structure. But if a process ID is specified, you can also walk through a first level paging structure, right, to maintain the same model of accessing memory that's assigned to a process, right, to translate that address. And the same way, once you resolve it to a system physical address, the IOMMU can invoke a separate IO entity checker to essentially resolve their address to a physical permission, right, for that resource. So no matter whether the access is coming from a RISC-V heart or from a processing element that's on an accelerator, you get very consistent permissions that you can apply for that supervisor domain, right? The other thing I sort of showed here is obviously this works in conjunction with the PMP and IOPMP. So those legacy mechanisms, if implemented, still are active and applicable, right? The other thing to call out in this slide, as the side arrows show, right? Depending on what modes are turned on a particular heart, you might have disabled first level paging, or you might have disabled second level paging. The MTT permissions still hold. So there are different modes defined in the MTT that tell you what mode you're running in and what physical address size, addressability you're supporting, right? That tells you, how the RDSM sets up those table structures. So let me jump back one slide that I skipped. So this supervisor domain extension, the best analogy to think of this is in RISC-V today, currently, for processes, we have an address space identifier, right? For VMs or with the hypervisor extension, we have the notion of a VM ID or a virtual machine identifier that lets you tag different structures that you might be using in the implementations, like TLBs or any address translation structures to optimize your access control permission enforcement. The supervisor domain essentially adds an analog supervisor domain identifier, right? So that depending on the memory translation or the memory tracking table permissions you're applying, you can also optimize how you're caching those permissions in the implementation, right? And to support that, there are new M-mode supervisor domain fence instructions described here or spec'd in the specification, which basically are shown here as the mfence.spa or the minval.spa. Those are variants to support different memory ordering models that RISC-V has. And I'll come back to the supervisor domain config register in a second, but the memory tracking register is sort of CSR shown in the top, which contains both the supervisor domain identifier, the mode you're operating in, and a root table pointer to the memory tracking table structure. So depending on what supervisor domain is activated by the RDSM on a particular heart, that memory tracking table can be made active in terms of its persona. So you could literally have a many core system with one core running in one supervisor domain when another core is running in a hosting domain or an alternate supervisor domain. So this view sort of shows a quick view of the SMMTT extension or the memory tracking table. The top view, I'm just showing the RV64 case here. There is an analog for the RV32 case that you can look at in the spec. But for the RV64 case, the physical address that's resolved after the page walk is essentially fed through this memory tracking table, right? Now, the memory tracking table that's defined here is very much biased towards large page sizes, so that we make sure like these permissions for these physical addresses are as compact as possible, right? They can also be supported in implementations by the right sort of caching structures, so that you reduce the amount of memory lookups you have to do for this memory tracking table structures, right? But net, you start with a PA or a system physical address, and for different page sizes, 4 kilobytes, 2 megabytes, or 1 gig, you essentially resolve that to a set of read-write permissions or read-write execute permissions for those pages. So you can essentially resolve any physical address to a full permission set, and then make decisions on that within the core. So I mentioned the IOMMU. I thought it makes sense to sort of put this in the slide just for completeness. So this IOMMU spec was recently ratified along with the advanced interrupt architecture spec. Both are now ratified, and people have been working on doing the Linux drivers and the infrastructure for it. But essentially the IOMMU, I showed you like the page walk earlier, is essentially the analog of the MMU on the IO side, right? It gives you a structured approach to essentially start from IO virtual address and walk through a set of device context and page table structures to essentially resolve to a system physical address that's subject to the MTT translation. So I just put this links here for people who are interested in looking at some of those specs. Right? So this slide sort of shows, once you sort of know how an IOMMU works and how it does a sideband look-aside to translate IOVA to a system physical address, this shows sort of one example of how an IOMTT side checker can be integrated into that pipeline, right? So when an inbound request comes in, it's resolved through a new entity here called a supervised domain classifier that will basically take a request type, like example of PCIe being a RID, and translate that RID to a supervisor domain, right? Which will essentially give you the context for that supervisor domain. And then you follow the standard MTT check to basically say, okay, once my IOMMU completes the task, of translating that IOVA to the system physical address, I can use the MTT checker to essentially make a decision whether that access is permitted for that domain or not, right? So this really helps in the scenario where the RDSM decides to give away a particular IOMMU or assign an IOMMU to a supervisor domain, right? So that supervisor domain can manage that IOMMU and all the devices downstream, right? And that sort of simplifies that whole model, that the RDSM doesn't have to emulate or arbitrate access to those IOMMU structures, right? But it can still maintain the isolation between different supervisor domains. I put in a couple of slides for a quick intro to the advanced interrupt architecture. Simply stated, like, the advanced interrupt architecture in RISC-V gives you the ability to route interrupts from an APLIC or a PCI device that's using message signal interrupts into a heart, right? And the way it does that is by using an IMSIC or an incoming MSI controller, right? Which essentially is a set of mode-specific interrupt files, right? So if you have no hypervisor extension, then you would have an M mode interrupt file and an S mode interrupt file, and so on. If you have a hypervisor extension implemented, then the AI spec sort of adds this spec for guest interrupt files, right? So you can have a heart implementation with a limited number of guest interrupt files behind it. Obviously, when you're using hypervisor, the IOMMU also needs to learn new tricks in terms of mapping the MSIs to go to the right guest interrupt files, right? So there's a MSI remapping that happens that the RVI IOMMU supports, right? Additionally, since that guest interrupt files are a limited resource, for over-provisioning guest interrupt files on CPUs or on hearts, you need the ability to be able to side back to offline certain interrupt files, right? So the RISC-V IOMMU supports the notion of memory resident interrupt files, or rather AI supports the notion of memory resident interrupt files, where you can essentially use atomic operations to take a guest interrupt file that's associated with a heart and move it offline into memory, right? The reason I wanted to go over this background is because you can see now, once you have a construct like the memory tracking table, which can isolate memory scalably between supervisor domains, you can also now scalably isolate whether it's guest interrupt files that are memory mapped accessed or memory resident interrupt files, right, to ensure that that interrupt isolation is also performed correctly for supervisor domains, right? So that's where this SMS DIA, which stands for supervisor machine mode supervisor domain interrupt assignment, comes in, right? So that's where this extension comes in, which essentially has the security objective for the RDSM to enforce the integrity of interrupt assignment to supervisor domains, right? So when you have a confidential domain, one of the known attack vectors is to confuse a confidential domain in terms of interrupt delivery. In fact, some of the recent attack papers were pointing out, like, hey, if you can like drop a particular interrupt or cause the rerouting of a particular interrupt or change the priority ordering, you can cause runtime issues in the confidential domain. So SMSDI essentially allows the RDSM to do basically two things with a set of very simple CSR additions, right? It essentially allows the RDSM to associate different supervisor domain interrupt files with the corresponding physical resource, and it gives the machine mode or the RDSM the ability to capture any pending notifications from supervisor domains that are offline, right? Because an external interrupt can come in at any time. So simply with these additions of a couple of these CSRs, as the red line shows, a new notification type is added for the machine mode that essentially tells it that an external interrupt is pending for one of the supervisor domains, right? So the RDSM can go interrogate these CSRs and can stage that for the corresponding supervisor domain. If the supervisor domain is already active and has been selected with this supervisor domain config selector, right, then that interrupt can be simply delivered by virtue of the right supervisor mode interrupt file being selected, right? And since the supervisor domain code already has access to that supervisor domain interrupt file, all those interactions that the AI defines in terms of accessing those CSRs, selecting the interrupt type, enabling it, disabling it, etc., those all remain exactly the same, right? So it allows us to flow through that interrupt following the same contract that the advanced interrupt architecture has, while still giving the RDSM the ability to cleanly isolate the interrupt delivery. So a little bit about the, I realize I'm running close to the end of time, but I think I have a couple of slides to cover. So a little bit on the Cove ABI. So like I said, a lot of the stuff that I covered so far were all the ISA mechanisms that we need to add for memory isolation, for interrupt isolation, for IO isolation, etc. But we also need to provide the right software interfaces between somebody implementing a TSM or the TE security manager that runs in the, as shown here in the HS mode of execution, and the operating system that's doing the resource management, right? So this model is actually very similar to models you might have seen in other architecture implementations, like Intel TDX has a similar model where you have a TDX module and interfacing with a Linux host or KVM host. ARM CCA has a very similar model where you have a RMM interfacing with the Linux host, right? So we've sort of modeled this interface the same so that it dovetails nicely into a lot of the infrastructure work that's being done in Linux, KVM, and all these modules anyway, right? And we've split those interfaces into a Cove H, which is the hypervisor side interface, and a Cove G, which is a guest side interface, right? And define sort of the interactions that we need behind those interfaces so that when you're doing, for example, memory assignment, where memory is being moved from a non-confidential domain into a confidential domain, the right intrinsics are put in place behind those flows in the TSM so that they can trigger the right ISA interactions, right? There is an open source project for people who are interested that was implemented by us. It's a Rust-based TSM implementation called Salus that's linked here. There's also a QEMU implementation of the SMMTT, the core ISA portions that's available in open source now. That was done by one of the students recently in RBI. And there's a new software security working group being formed in RISE. RISE, for people who don't know, is a sort of a RISC-V software ecosystem, consortium that's been put together to help people working on RISC-V to sort of work on common things like code infrastructure, build systems, things like that, looking at different distributions. So there is a security work group being formed there as well to bring together some of these common elements, like, hey, if I'm writing an RDSM and I want to write it in Rust and make sure it's open source and well vetted, can we do that together as opposed to everybody writing their own, right? I won't really get time to go through a lot of this, but I wanted to introduce this Cove IO stuff, right, which is sort of new interfaces or ABIs that we need to add. A lot of this work is being done right now in the Linux open source domain, along with other implementations in this generic framework called TEIO, right, of how we take device functions that might be on an accelerator and bind them to a TVM, right? So there is this whole flow defined here of how does a host OS expose a device to a TVM, right? How does the TVM authenticate the device function, and how does it go ahead and accept that device function into its trust boundary, right? So this is a very common flow across many of the implementations that are happening across other architectures as well. So there's a common working group in the Linux Coco work group, if people are familiar, that's been discussing this thing and how do we use the standards that are coming out of PCIe, like IDE, which stands for integrity and data protection between the PCIe endpoint, right? As well as TDISP. TDISP is another sort of standard for if I have a device function, how do I in a standard way assess the state of that device function? Is it like is its configuration locked down for me to start using it, right? So TDISP sort of sets up a set of verbs that you can interrogate a device and put it in the right state for being used by a TVM. So that's a newer spec for RISC-V as well. It's in its initial stage of 0.2 version, and we are sort of building that in conjunction with the Linux open source folks who are looking at the common verbs for that. Last but not the least, some of the hardware root of trust is an important capability from an attestation perspective. Again, here we are relying on a lot of the standards that people are putting together for attestation. Attestation has been worked on in the IETF for a while, as well as in the TCG, the Trusted Computing Group. There's a standard that TCG put out called DICE, right, which stands for Device Identity Decomposition, which is basically a layered attestation model. It's essentially when you start from a hardware root of trust, how do you ensure that the hardware root of trust itself is trusted, right? Its configuration has to be, explicitly endorsed by the silicon creator. And then how does it go on and measure other elements of your TCP and capture those measurements in a way where you can cryptographically verify from a relying party, right? So that whole attestation process, we're trying to make sure we use a lot of the existing standards that and common frameworks that are being built there, so that we are not reinventing the wheel there. In terms of the RISC-V itself, there's a good engine for people to look at called OpenTitan, which is basically an open source secure silicon built using a RISC-V core as the main control processor. So if folks want an example of, okay, how is RISC-V being used in that domain, right? But that is one of the important building blocks from a confidential computing perspectives. Couple other things, I guess we talked about other threats on the platform. We won't get to cover a lot of this, but I wanted to call attention to these. Like when you're building a platform that is being applied for confidential computing, you need to have a very clear story around, how do you deal with invasive debug? Like, think of like tracing frameworks or external debug frameworks. How do you deal with machine monitoring frameworks like QoS, for example? And some of the mitigations or design patterns that can be applied there, obviously using cryptographic protections when information is leaving the package, right? So things like using memory encryption for DRAM or PCI ID is another good example for data fabrics like PCIe. Filtering by specific supervised domains, we're providing some frameworks, for example, for external debug and things like that to be able to filter by supervisor domain. Opting in when some of these capabilities are turned on for a particular supervisor domain or a context within a supervisor domain, opting in and making that information explicitly aware in the attestation is a good way to also tell a relying party like, hey, this TVM that you're interfacing with has debugging turned on. Do you still want to share your data with this TVM? You probably you can make a policy choice to decide whether to do that. And then lastly, restricting access or enforcing access or configuration through the hardware root of trust, for example, so that you know that the configuration of that fabric or the configuration of that subsystem can truly be trusted. Right? So those are some sort of methods of mitigation, I guess, that we've been looking at for those aspects. But a lot of these are very implementation-oriented, non-ISA aspects, so we leave those as recommendations in the security model for people to look at from a implementation perspective. Right? So just to summarize, I touched upon some of the ISA mechanisms in a little bit more detail, but I hopefully gave you a good flavor for like where some of these extensions are going and some of the software interfaces that are being built as well. And hopefully there's enough information for people to go look at and follow through. The last, I guess, call to action I had was, we think this is an important capability for really any platform that is going to operate on sensitive data, especially more so in the space we are in with things like confidential AI. And there's like a number of task groups that are actively working on these ISA and both non-ISA aspects. So I'd welcome folks to come and join those TGs either as individual members or as members from organizations that are part of RISC-V. And you can also participate, if you're not part of RISC-V, you can also participate in some of the open source domains where, like Linux and KVM and others, where we are discussing these intrinsics from a, turning on these capabilities or interfacing with other subsystems in Linux. So a lot of work remains to be done, and I'd welcome this community. Especially from a security perspective, it really helps to get more eyes on it, as Renee pointed out earlier. So with that, I thank you for your attention. Like I said, there's a lot of people involved in the task groups from various organizations and individuals. So I wanted to give a shout out to them as well. Thank you. So the question was, does the secure interrupt stuff apply only for physical devices and not for virtual devices? And then I think the second question was, does it also apply to IPI and things like that? Yeah, so I'll take the second question first. Yeah, it applies to IPIs and things like that also, right? Because those are all routed through the same mechanisms. In terms of physical devices, virtual versus virtual devices, so from a general virtualization perspective, right? Even if you look at like nested virtualization, for example, right? From a hardware perspective, there's really only two levels, right? There's physical and there's virtual, right? Any virtualization above that is sort of a software contract, right? So yes, the secure interrupt stuff applies to physical devices, right? But if, let's say you're assigning a device into a supervisor domain through an IOMMU, right? Including the IOMMU, right? Any virtual contacts that are running on top of it are really being managed by the TCP software in that supervisor domain, right? So think like, let's take the example of a NIC. If you have like a SRIOV NIC, right, that's behind that IOMMU domain, and you assign that to a supervisor domain, that TSM is free to virtualize that NIC to other workloads above it, right? And that's really the control point is that supervisor domain software or the TSM inside that supervisor domain. So it can scale that up for other virtual interfaces. If you look at other new capabilities like scalable IOV, for example, right, which is sort of being discussed in OCP and other forums, it's sort of the same kind of model, right? You have a set of work queues assigned to some context, some workload context, right? It's still your mediating software that's breaking up that workload really becomes part of your TCP, right? So yeah, once you do your physical assignment, your next level multiplexing is owned by that TCP software that's in your path.
But you have to do physical assignment, so on the host you can't have, you obviously can't apply to virtualized devices on the host, like virtual stuff on a host. That's out of question.
That's right. So if you're in a situation where you have to rely on the host software for the virtualization, then you have to use some other logical protection mechanisms for the data that's going to that channel, right? It's like, that's kind of like what we would do before we had an ability to pass devices through. You would rely on some emulated device, but then it's like using virtual block storage or virtual networking. You have to make sure your SSL endpoint is running within your confidential domain, right? So that the transport is essentially untrusted. Yeah.
Could you share some details on hardware root of trust? That is, how is that achieved in terms of compiled with ARM?
So the hardware root of trust, I think, is sort of like orthogonal to the ISA mechanisms I talked about here, because your hardware root of trust could be different implementations, right? There are some like critical requirements on the hardware root of trust that you want to have, right? For example, you want to make sure you have a subsystem in the hardware root of trust that can implement DICE, for example, right? Some engine that can hold keys that are associated with certain identities that you're building, right? And you might have an identity for the silicon creator, you might have an intermediate identity, like I'm using OpenTitan terms here, for like a silicon owner, right? Or the entity that programs that engine. You might have an identity for a platform integrator and a platform owner, right? So you need to be able to have an engine that supports these different roles, right? I think it's up to the implementations to choose different engines that give you that capability, right? So OpenTitan is like one example that I gave. There are others, that people use, but it sort of comes down to, do you have the right primitives on that, that root of trust, right? That gives you, I think TCG uses the terminology of like, do you have a root of trust for measurement, right? Do you have an entity that can hold measurements as you're evolving the platform and booting up different capabilities on the platform, right? Do you have a root of trust for storage, right? So that you can do things like sealing and unsealing secrets to the platform, right? Things like that, right? So, yeah. I'm getting a red flag from the back to stop for lunch. I guess, no, for the next talk, actually. So yeah, please ask me other questions if you might have. I'll be here both the days. Thank you.
Okay, thanks, Ravi. My name is Mikko Ylinen. I work for Intel, and I've been working on confidential computing and various cloud-native technologies for the past few years. And in the intersection of those two, I've been working on a project called Confidential Containers. That's part of the CNCF, Cloud Native Computing Foundation. Ravi gave a good introduction to confidential computing already, and there was a good question about how many of you in the audience know about confidential computing. My observation has been that not too many people raise their hands when this question is when this question gets asked. It was good to see so many hands raised up. I would like to ask a follow-up question to that, is that how many of you have actually started to adopt confidential computing in your daily work? Not too many. That's good, because part of my talk is what I'm trying to achieve here is that okay, how do we make this confidential computing adoption easy for the applications that exist today? I've been hearing a lot of these comments, and I've been participating quite a few discussions whether we would need to have dedicated user space or user library APIs for the workloads to take advantage of confidential computing. And my observation just recently was that, hey, maybe we don't actually need to do that. We have pretty compelling existing APIs provided by the kernel that we could maybe take benefit of. And that's basically what my talk is about. So Linux Keyring seems to provide the necessary functionality for at least certain use cases that are kind of relevant for confidential computing as well. I had initial offline conversations about this particular topic, and I got some positive signs that, hey, this could work, sounds okay, but of course it depends on the use case. So I have a couple of use cases that I want to show you. My talk, by the way, I forgot to mention, this is in the short talk category, where the idea is that I spend roughly 20 minutes or so talking about the actual topic, and then we could have 10 minutes for discussion. Let's see how that works out. I'm between you and the lunch. Let's see how that plays. But let's say I'm also available for the BOF session later on. I could maybe even give you live demos about the setup that I'm talking about today. So just let me know. Timing-wise, fortunately, my agenda also includes very basic definition of confidential computing. I'm able to skip some of those because they were covered by Ravi in the previous talk. I hope I have some gaps to fill, especially in the areas of attestation and some of the details what goes into the attestation. I'm also going to, of course, give a high-level overview of what this Linux Keyring functionality is about. I have two use cases covered that sort of highlight or showcase the idea that I've been thinking. One is about disk encryption, and then another one is about how workloads could seamlessly attest to get attestation tokens into the confidential environments, TE environments. And at the end, summary, call to action, and hopefully a bit of discussion as well. I'm going to skip the basic definition of what this confidential computing is about. There were quite nice examples covered why this is needed. Very commonly or where confidential computing is emerging these days, of course, is like cloud environments. So it allows workloads to move to clouds without worrying about like your friendly CSP tampering your data. Confidential computing builds on top of the TEEs. Attestability is really the key, so that you actually get to verify remotely, remote attestation in particular, remotely the state of your TEE before you get to inject your secrets, or before you get to provision your secrets into the runtime environment. Of course, TCP is an important aspect as well. A vulnerability in your TCP, inside your TCP, may break the security of your system. That's why the goal should be that design for a small TCP to make the likelihood of bugs getting in your TCP slightly smaller. If you look at concrete examples how this confidential computing shows up in data centers today, and what it actually means if you do not have confidential computing. So elements with potential access to your confidential data. Without confidential computing, your whole platform is basically your TCP, and even your host admin, host operating system can potentially get to see your confidential data, whether it's running on the host or in a confidential virtual machine. There are TEE technologies that allow you to isolate the TEE to a very small size enclave. It could be even like a library level TEE that you have like a very small TCP, and then outside your TEE you have quite a lot of components. What's the focus of my talk today is when you're adding a VM isolation, confidential VM isolation to the mix. With confidential VMs, you basically, what's outside your TCP is all your platform owners, BIOS, firmware, and also the host operating system and the VMM hypervisor. And you get to control what goes into your TCP by defining what is in your VM guest operating system and the application data in it. A bit more about attestation. So there is a group under the IETF working on defining various aspects of remote attestation. The working group is called the RATS architecture, or the RATS stream, remote attestation procedures. I'm using some of their material just to define the terminology that I have in my use cases later on. What's really relevant here is like what is the attester role in the picture. So attester is in this case the confidential VM or the application running inside the confidential VM. The attester produces evidence for the verifier, someone who checks that, hey, okay, if the TEE environment is what it's expected to be. The verifier uses various sources of information to actually make sure or check against whether the TEE environment is a legit environment. The verifier can produce attestation results, and then some relying party can use the attestation results to make the final statement that, hey, okay, the attester that originally produces the claim was indeed a legit TEE environment. In addition to these roles, oops, what's wrong with the, sorry about that. In addition to these roles, there are different type of topologies how this attestation takes place. Two of the most commonly used topologies is the background check mode, and then another one is the passport mode. There are, of course, like hybrid variations of these two, but these are the most commonly used and something that I'm using with my use cases later on. So let's take a closer look of the topologies. In the background check mode, the flow works in a way that the attester produces the evidence from the TEE and sends the evidence to a relying party. This relying party could be an application who, for example, keeps secrets. It could be like a HSM, key broker service, who needs to verify or make sure that the attester or the application running in a TEE who wants to get some secrets provisioned is indeed a legit TEE environment. But the relying party application itself doesn't know what to do with the quote or what to do with the evidence. So the relying party can then sends the attestation request to the verifier to check whether the evidence that was provided was something that should be trusted. And then the verifier checks for the hardware evidence, and then it can provide the attestation token back to the relying party. And then the relying party can still do final checking and evaluate the attestation results against some custom local policies before responding to the original request from the attester. With the passport modes, it works slightly different. So the attester talks to the verifier directly. It could include a nonce from the verifier for the freshness purposes. The attester collects the evidence and sends the attestation request to the verifier. The verifier again checks the evidence, but in this case, the verifier returns back an attestation token to the attester, and the attestation token is then what the attester uses with some relying parties to say, hey, I have my password, this has been verified by the verifier X, I need to get some services from the relying party application. Again, it could be like a key broker service. The relying party then checks for the token again and responds back with the request. So that's about the confidential computing and attestation side of things. Let's move on to the keyring side of the things and talk a bit about what this Linux keyring mechanism is about, and then I'm going to show you how the confidential computing and attestation can be combined with the keyring functionality. Keyring is an internal functionality to store security-related data. It could be like keys or tokens. I think the history is that it was originally implemented for the kernel components to store and use secrets or security-related materials, but it is also possible for the applications to use the kernel mechanisms to store and retrieve key data inside the kernel. The keys definition is that each key in the kernel has an ID. It has a description, some free text format of description that identifies the key. Of course, it has a type. There are different types. I'm going to those types in a moment. Payload is basically what the content of that key is. and then access control mechanisms, how long the key is valid, and who is actually using the key for reference counting gives that information. Different types of keys, basic types, user key, logon key, big key. Big key is just like a key with a bigger size in the kernel storage. And then key can also be a key ring, and key rings are what the kernel uses to anchor the life cycle and permissions for a key. There are different types of key rings in the kernel-like process. What this key ring type of process allows you to define is that, for example, certain process in the user space only has the access to a particular key that is that can be found for the key ring, or even in a way that it can go to the finer granularity that a thread in the process, only one thread in the process can access a particular key. There are also different other types of key rings, like persistent or some special key rings that are only reserved for the kernel internal functions. What makes this interesting, of course, the user's perspective and the application's perspective is that there are system calls available to manipulate these keys. So the user land can use the syscall add key to add key. Key control syscall allows you to manipulate certain key parameters, like who has the access to a particular key, how the key rings are linked to each other, how the keys are linked to various key rings, and so on. And then finally, there's a request key system call, which I've found is pretty interesting for this use case that I'm talking about. So a user can, with this request key system call, they can request keys from the kernel key store. Here I have the key utils wrapper. This is how it looks. So when the application wants to access a key in the kernel key store, it just specifies what type of key the application is looking for, what's the description of the key. The caller can also specify like additional call out information to specify or to bypass additional information, and then the destination key ring, what is the key ring where this application wants to have the key available. So and how kernel works when it gets this request key command? If it of course tries to find the key with the requested parameters, and if it's not available, if it cannot be found, it just returns like an error code that I have no key for it. Or alternatively, if the key is available in the key store, it returns the key ID that the application then can use to do whatever it wants to do with that particular key ID. User can affect how the key is. So there's an additional use case or there's additional functionality with this request key functionality, is that if the user has specified this call out information that is not as null, and the kernel cannot find the key, the kernel has a mechanism that it actually can call out to the user space using this request key helper, trying to find someone in the user space that can actually instantiate the key. And it's more like it's like a plug-in mechanism that the VM owners, in this case the VM owners, can specify configuration, like where to try to find those keys. It can be there can be a plugin provided by the VM owner that, hey, actually this particular key can be found from a remote HSM or a key broker service, for example, or some other use case specific mechanism. And how this works, like on a very high level, to put it in a sequence diagram. So we have the key ID user calling the request key. The kernel tries to find the key that was requested by the keyring user, cannot find it. The kernel issues the call out to the user space. And then in case of confidential computing, now we are getting into the kind of the beef of my talk here. So what we can do to hide some of the attestation details from the application who was using the keyring functionality is that we can have an attestation aware upcall provider that knows, first of all, how to generate the hardware evidence from the TEE environment, and then reach out to some relying party or some verifier to get some secrets provisioned into the kernel. Here I'm using the confidential containers projects. We have a simple key broker service client that is at attestation aware, and this key broker service client knows how to talk to a key broker service with the attestation handshake happening between the two. And the KBS client in this case has all the various hardware TEE has all the hardware TEE functions added, so the KBS client knows how to generate the hardware TEE specific evidence on the platform that it is running. The KBS client issues an attestation, or let's say it could be like a get me a secret type of call to the key broker service, and the attestation happens, attestation verification happens, evidence verification happens, and then if everything works fine, then the key broker service returns the key back, and then the upcall provider then instantiates the key into the kernel. But really, from the application adoption perspective, like I said, the application only needs to know about the keyring request key, syscall, and then everything else, including the attestation, is abstracted behind the keyring functionality. And then let's take a look of two different use cases. So one use case I have with the crypt setup and encrypted disk passphrase retrieval from a remote key broker service with attestation. So first of all, why we need, or why it's important to have your virtual disks encrypted. So if we go back to the trust model again, some of the elements of how the virtual disk data gets committed to the host goes through untrusted pieces. So it is the responsibility for the VM itself or the application to make sure that you have your data encrypted before it gets stored on the disk on the host side. So we need disk encryption for confidential virtual machines in quite many cases. Crypt setup tool, many of you are probably familiar with the crypt setup tool to play with the looks functionality. Already knows how to read key slot passphrases from the kernel keyring. Unfortunately, it doesn't, as of today, use this non-null call out information, which would basically transparently allow crypt setup to be hooked into these upcall providers. But it can be worked around in a manual way. So I have a bit of bash commands here, first showing that, hey, okay, we have no keys in the root user's default session keyring, but using the key control utility and with the proper configuration, I can use keyctl requests, test passphrase, and then behind the scenes, the configuration of this particular VM that I was using fetches the test passphrase from a remote key broker service with attestation. And this setup here basically follows the background check at attestation topology, where the crypt setup application and the key broker service client talks to a remote relying party key broker service, and then key broker service uses a verifier to check the hardware evidence, and then only if everything passes, the test passphrase gets provisioned into the keyring. I've done a bit of my own experiments with this functionality, that if I'm changing the crypt setup a little bit to have a non-null call-out information in the code, this actually works in a way that, hey, we don't have to do this special custom keyctl request command anymore, but the crypt setup itself can be just issued crypt setup open, and once that crypt setup command is issued, the kernel keyring and the user space callout gets the test passphrase into the keyring transparently behind the scenes, and then it's just possible to get the encrypted volume mounted. Another potential use case for this one is following the passport mode, where the application needs to get an attestation token generated. But in a way that the application itself doesn't know what format or what is the right format, or how to compose the right attestation token format, or whatever is the verifier configuration even. So it could be that you have two different virtual machine builds. One is configured to use one verifier, another one is configured to use some other verifier. So this is something that the application doesn't need to know about. And also, like, the application doesn't necessarily have to know about how long the attestation token is valid. So typically the verifier sets the token to expire after 30 minutes, 15 minutes or so. So the application doesn't have to have the logic of, okay, I need to request a new token after 15 minutes. This is everything what the keyring can actually offer. It can cache the token as long as it's valid, and then if the application requests a new token, if the kernel has detected that, hey, this token has been expired, let's get a new one with the TCP status re-evaluated after that time period. And then here I just have a simple example how this works. So again, using the confidential containers functionality, so the CoCo trustee setup knows to return JWT attestation tokens back. So the application is just requesting CoCo, give me a CoCo token, and then in the keyring, it just gets the access to a JWT token that is issued the CoCo attestation service, and then, for example, that the DEE environment that this test was run is an Intel TDX environment. Okay, so that pretty much concludes my talk and everything that I wanted to cover. So I was able to show you like how it's fairly easy to hide some of the attestation details from applications, hopefully in a way that it's easy for the applications to start consuming confidential computing in a way that it's like not too intrusive, that the applications would have to modify. So applications based on this can just use the existing kernel, unmodified kernel keyring functionality to at least get some of the basics covered. All of my code setup and everything you can find from this GitHub gist that I made available. But now it's time for questions, and I'm looking forward to hear feedback from the audience, if this made any sense, or if you can think of any additional use cases that would be interesting to explore. I have one more that kind of links to the supply chain topic. So this is something that I didn't originally include into my presentation as the use cases, but just Friday last week I was exploring how the asymmetric keys functionality can play with this setup, and that also seems to work. So it is possible to use the keyring functionality to store asymmetric keys, and what's nice about this asymmetric keys setup is that you can do, for example, code signing with the private key completely in the kernel, and in a way that even the application doesn't have the access to the private key side of things. So it can only use the keyring services to do code signing, but won't have the access to the private key itself. Good. No questions. I guess just like I guessed, so it's the lunchtime now, so. Oh, there's a question?
Yes. Actually, two questions. Question number one, have you thought through whether all what you suggested runs in the early process?
No. I'm still in a very early exploration phase. One thing that I, by the way, forgot to mention about this, the benefits of this setup is that it allows me to implement all these key providers and attestation functionality using what we are using in the confidential containers, is using memory-safe languages and Rust-based setup. So if you have an application, legacy application, Python-based, it could still be able to use Rust-based setup to deal with all the attestation pieces. But no, yeah, no, just like I said in the beginning of the talk, I'm just early exploring the use cases, and I would be very interested in following in a BOF session, perhaps, if you have ideas how this could be taken further.
Next question, how do you make sure you're talking to the right key broker if your plugin asks for keys?
Yeah, that's something that the VM owner needs to decide, and whether the configuration actually gets measured into your quote that, hey, this is the right, the VM was booted using the right configuration that was expected. Good.
I'm assuming we're inside a confidential meeting. So, this trusted thing here, right? Is that inside the same VM or is it outside?
This one?
Yes.
Oh, this is outside.
Okay, right. So I need to be able to set up an encrypted session, connection between these two. How do I do that? I've got a bootstrapping problem because I need to be able to create material so I can actually create. Does the mechanism by which the keys are created allow for encrypted connections between the two? That call you made, right?
Yeah. So I'm going to just.
This has got to be encrypted. This connection here, right? But the call you make, which is this call. Let's call it. It's just okay, where was the show the method you called? The request key. Yeah. So either this needs to be possible over an encrypted session, or we need to establish some way of encrypting the key, but we can't do that because we've got a bootstrapping problem. Does that make sense?
This is, yeah, well, this is what the application calls. The application doesn't know anything what's happening.
Yeah, sure, but okay, so maybe not that one, but
yeah.
Do you see what I mean?
Yeah. HOCO, we have this KBS protocols, obviously have handshake. So first of all, we have the DLS of your KBS part of what gets measured.
But you can't set up a trusted TLS connection here, because this has got to be sure that it's giving it to the right thing here in the first place, right? Let's do this another time. Very interesting. Can I contact you on LinkedIn maybe, and let's talk.
I have this follow-up on Thursday.
Oh, you're doing the same talk. Well,
which is actually the reason why I thought I could check with you on the potential changes.
Okay. Well, let's. Looks like someone else has got a question for you.
That's okay.
I think we're going to have to. I need to do some sketching and doing stuff down. So you talk to me, go first. Yeah.
Just have a little bit of, will I say, trying to, from this level, if you want to go lower before coming to this level, what do? Because you just abstracted it from the advanced level, and you want people to get the contribution into confidential when we didn't have some basis of how to start the use case from the scratch.
Oh, okay. Microphone works. Hello, my name is Reinhard Bündgen. I'm from IBM, and well, I'm an architect working on crypto and on confidential computing for Linux on the IBM Z platform. And my task is to keep you awake after lunch. The talk is about hardware security modules and confidential computing. So, well, I know there are quite a few who are concerned about and knowledgeable about confidential computing. Here's my question: who knows what a hardware security module is? Very good, I'm impressed. I will give, nevertheless, a small intro on hardware security module and on my personal view on hardware security modules, as well as secure execution, but I keep it fast because we want to look at the combination, which is non-trivial. Okay, what's a hardware security module? Some hardware device performing crypto in a secure way. In a secure way meaning that it protects key material. Yes, the key material means the keys are never visible in plain text inside a computer system. They are protected, and there are two methods to protect them. Either the hardware security module has some wrapping key inside it that is used to wrap all operational keys, or the hardware security module has a big table of keys and identifiers that can be used by the program. These are the two methods I am aware of. If someone knows the third one, I would be interested in learning it. Okay, a good hardware security module is certified, typically against FIPS 140-2 or 3 these days. It's temper respondence, and therefore it needs level 2 and above. Yes, and the idea of a hardware security module is to render key material, a key object, useless without the access to that very hardware security module. Well, confidential computing, we know it's about running a piece of code as a black box inside of some hosting software. A black box means no state of that piece of code is known, and I think today the majority of confidential computing solutions for this piece of code is a virtual machine. That makes things easier. The only confidential computing that I'm aware of that is different is Intel's SGX, which can go with arbitrary pieces of code. And you see all major hardware providers have a confidential computing solution. Just over lunch, I added the last one, RISC-V. Yes. What is confidential computing about? About confidence, about trust. So that is my world of cloud computing. There are the olden days where the customers has a traditional trust model, and it's about policies, about contracts. The cloud clients just believes the cloud provider that the cloud provider is doing the right thing. He has some kind of contract with the CEO. The CEO inside his organization has hopefully policies to convince the operators to do the right thing. And the CEO, again, trusts the hardware provider. With a confidential computing model, that's different. Oh, well, I should say, given that model, whoever attacks the operator, be it that he bribes the operator, be it that he threatens the operator, has a chance to get inside the provisioned software, even if the cloud provider originally is a good guy. With the confidential computing trust model, the idea is that the cloud client only trusts the hardware vendor. That the hardware vendor, of course, needs secure supply chains inside, have also its policies that things work fine. But after all, it's only the hardware vendor. The cloud provider has no influence in looking into the workload. The only thing, and it was mentioned before, that you cannot protect against is a denial of service attack. The easiest one of the cloud provider would be just not start the workload. Nothing we can do about it without complicated cluster mechanisms, of course. Okay, why do we use HSMs? And what is the essence of an HSM? Well, the sad answer is, I guess, 90% or even more of the companies who use HSMs do use HSMs because they must. Some legal obligations require them to use the HSMs, and they won't just have the check mark done. But there's a security reason behind HSMs anyway, and that is why I am talking at a security conference about HSMs. An HSM is a means to protect cryptographic keys from being used outside of your system. Yes? So HSM is about security, about securing keys, but it does not help you if some intruder somehow gets into your system and uses these keys, these key objects inside your system. Because inside your system, you would have access to your HSM that is connected to your system. So an HSM is mainly a protection against what I call an offline attack. Someone somehow gets hold of your keys, steals them, and uses them on their own system. How could you steal a key? Maybe a key stored on an unprotected disk. Maybe with an attack like Heartbleed that you could just extract some memory from a system, possibly without you realizing it, that it happened. Doesn't matter. And so that is the kind of protection. And in that case, the key or whatever key material is stolen must be useless. And therefore, the HSM must be something that you own, something that only you can use when you have access to your HSM. It's a device that renders stolen keys useless. Just as a simple example, we have an application that encrypts some data, sends end-to-end encryption, sends the end-to-end encrypted data to a storage server. If an attacker steals the brown encryption key, he could sniff the wire or even get to the storage server, get the data, and decrypt it. Now, if that key is protected by an HSM, that's the violet ellipse around the key, the protection, then a thief who steals that key has no chance to use that key outside of the actual system that is connected to the HSM. So what is wrong with using a HSM in a non-trusted cloud? Well, the stealing of the HSM is so easy, in particular for the providers of the cloud, for the operators of the cloud. It's just a matter of reassigning the HSM to another system. It becomes particularly simple in a virtualized system. When it's just a management operation, you do not even have to replug an HSM. And well, some HSMs are plug aware, so they would destroy themselves if they get ripped off a machine. In a virtual system, it's just a piece of software layers informing the firmware route the traffic to a certain virtual server. So stealing an HSM is very easy in a virtualized system. What's even more, what's a virtual system? But we can get to that later when we look at the attacks that are possible. Now, we could use a PIN. Remember your credit cards? They are protected against stealing with a PIN. But, well, in a server system, sorry, I'm coming from a big company. We are not dealing with PCs. Our customers want to have these huge things. And they run multiple servers in a server farm on a system. So interactive entry of pins is a no-no on such server systems. And even that would leave a little period of time where there could be an attack. So we must store the pin somewhere. Well, and storing the pin somewhere without a special protection is like writing your pin on the back of your credit card. It can be stolen. It could be stolen as easily from your system as the key material can be stolen. So, next option, network HSMs. Well, in order for the network HSM to be owned by you, you must authenticate yourself to your network HSM. Well, we know, hopefully everybody in this room knows, to authenticate without a physical secure connection, the only way is to have some secret, to have a protocol based on a secret. Where do you put that secret? It's as typically as easily stealable as your key material, and we have the same problem. Yes, you can put the secret on a stored disk, and the key to secure the disk must be then somewhere, so we get this infinite recursion. So we have that problem that cannot easily be solved. Before we look into a solution to this problem, I want to describe 3 types of attacks to you. Attack number 1 would be just to, these are attacks that work in a virtual server. So HV stands for hypervisor, and what I call guest is what other people call a virtual machine. We have this guest that is connected to an HSM. Inside the firmware, there are the request queues. You can imagine, since these are typically plug devices, so they are asynchronous, you send a request and get a result that you can fetch at a later point in time, typically. So what can happen during the operation of my guest 1, even during the submission of a request, that the ownership of or the access to the HSM can be switched to a different guest. So that guest A sends a request to the crypto card, and guest B could read the result. That is something we have to protect against. Or any other kind of that would allow guest B to sniff to the communication of guest A with its HSM. That is attack 1. Attack 2 would be, well, a double attack, namely the stealing of the secure key object. I put the green, dark green ellipsis is the binding of the key to the master key in the HSM, the wrapping key that's in the HSM. I could steal that key, and at the same time, I could steal the HSM, in which case I could use this secure key on the attacker could use the secure key on the HSM. That's another attack. The last attack that we have to deal with is if someone prepares an HSM with the master key that this attacker knows, and then lets you use the HSM of the attacker, so that you run your software with the wrong HSM. You think your keys are protected, but they are protected in a way that an attacker can interpret the keys. Okay, let's settle these attacks a little bit. I will come back to them. Before I get now into the solution, I have to talk a little bit about the kind of hardware and confidential computing solutions we have on IBM Z and Linux One system. Our HSMs they are pluggable cards. That's a picture of them. They are they can be used as HSMs, and they are prepared for virtualization, so they can be configured to be up to 85 virtual HSMs. So they have different partitions. Each partition has a partition-specific master key, and these virtual HSMs can be assigned to different virtual machines. And we can actually talk to the virtual machine can talk to the HSM in pass-through mode. So that's interpreted by the firmware directly and not intercepted by the hypervisor. Okay, I mentioned already we use the type with the master key, where our secure keys are actually keys, operational keys wrapped by the master key. The assignment is done from the system itself, and yes, we have a master key, so it's something that's configurable. Therefore, I should shortly mention how such a HSM is configured. We have something that we call Trusted Key Entry Console. That's a lockdown computer, if you so want. This is the plate form factor that comes with smart card readers and smart cards that allows you to configure the domains of our CryptoExpress adapters. There's a secure channel between this Trusted Key Entry Console and the actual HSM, the plugged-in HSM. The admin of a domain can generate the master key in multiple parts. That allows to have a multiple I policy running, and these are either generated on the smart cards or on an HSM that's inside this Trusted Key Entry Console, and then via a secure protocol it's sent to the card, and the card is configured that way. One thing, in a solution where the HSM should be used in the cloud, the admin of such a domain, must be trustworthy. Yes, if there's a trustworthy domain admin, that non-trustworthy domain admin could somehow implant keys that he more or less knows, and that is detrimental to your security. So next, a few words on secure execution for Linux. That is the confidential computing solution for IBM Z, and as the name says, it only works with Linux and Linux KVM as a hypervisor. I think different to most other solutions, secure execution can start encrypted guest images. So the images can already contain a secret. The firmware layer that implements a trusted execution environment is called Ultravisor. On IBM Z, the Ultravisor has access to the root of trust for secure execution, which is a so-called host key. That's a private key of which the public key is published, and each image is generated with the help of the public key, and only the Ultravisor can interpret the image and get the image encryption key, and then starts the secure execution guest. I think that is, well, other than that, of course, for a secure execution guest, all state is protected while the secure execution guest is running. In a later release, in the current release of our hardware, we have support for remote attestation. The interesting thing about that is, as a result of the remote attestation request to the Ultravisor, you get a unique configuration ID that is a unique ID of the running guest instance. That way you can check whether two guests that you connect to are actually the same instance or not. Okay, given the confidential computing promises that you do not have to trust the hypervisor and hypervisor admin or hardware admin, we didn't implement HSM support to begin with, and this came only recently, actually spring of this year. So, how does the solution look like? Protection against attack number 1. This protection establishes a binding between a guest and the HSM. Now, we have to understand such a binding isn't possible without confidential computing, because how virtualization works is that actually the hypervisor maintains the guest. So the hypervisor maintains all the significant things that make up the guest, the page tables, the pages, the CPUs, all the states. And since the hypervisor manages this, with every interception, the hypervisor can actually remodel the guest as it wishes. A malicious hypervisor can do everything with the guest. So from a system perspective, a guest, there's no crypto guest. That changes with confidential computing. There must be some firmware, typically around making up the trusted execution environment, that maintains the guest, that keeps the memory unmodifiable by the hypervisor, the CPU setups, and all other kind of state. So now, all of a sudden, the firmware has something that makes up a guest once the guest is started. So it can establish a binding between a guest or between all the structures that the ultravisor maintains to specify the guest, and that the hypervisor cannot modify. And once a HSM is bound, no other guest can access this HSM as long as the binding persists. As another measure to make sure that a secure guest cannot mistakenly talk to a HSM that is not bound, the ultravisor will disallow any communication between the secure guest and a HSM that is not bound to that secure guest. Okay, there are of course means to forcefully move the HSM to a different guest, but that implies a reset and will automatically undo the binding. And undoing the binding comes with a reset that will clear the communication path. So it's kind of can be a denial of service attack, but it will not be a security leak. Yes, if you don't have an HSM but just an accelerator card, that is sufficient, that binding, to protect against attacks. Attack number 2. Here things become a little bit more complicated. Remember, attack number 2 was this double theft of the HSM and the secure keys. Or what we do here is we let the ultravisor maintain a secret, we call it association secret, and we bind the keys not only to the master key, but also to the association secret. And the ultravisor enforces that all requests to the HSM that involve a secure key must be can only be sent to an HSM that is associated with this association secret. What we technically do is we set up a session in our EP11 adapter, but that is something if you can ask me about during the breaks. So the association, okay, and secondly, whenever a key is generated in an association in an associated HSM, then that key is bound to the association secret. Other than that, whenever you reset an adapter, when you unbind an adapter, the adapter is implicitly also deassociated. So the session is stripped down. And clearly, you can only set up associations if you have first bound the adapter. Yeah. Note, association is only needed for requests that contain a secure key. Either a cryptographic request, please sign, please encrypt, or a key generation request where the secure key is in the result. Some management requests, including setting master keys, can be routed to adapters that are only bound and not associated. And of course, queries to the crypto adapter. Who are you? What is your master key verification pattern? Just to find out what HSM do I talk to. The last attack is something firmware cannot do much about. It's something that the software has to deal with. Namely, whenever you want to trigger an association, you better make sure that the crypto adapter is the one that you think you're talking to. The master key verification pattern, which is some kind of hash or an encryption of a predefined pattern that characterizes the crypto configuration, can be used for this. So for our crypto adapters, there's a sysfs entry where you can find out the master key verification pattern of the system. And if that is the one that you are expecting, you can do the association. For OpenCryptoKey, which is implementation of the PKC's 11 standard, for the HSMs that we support, these are the EP11 adapters, we have a configuration that allows the EP11 token to only let key generation functions succeed if the resulting key was generated with the right master key verification pattern, which is inside the key, which is inside the readable part of the key. So, next problem. I just postulated there is some association key in the metadata of the secure guest that the ultravisor maintains on behalf of the secure guest. That key has to, or this secret has to get into the ultravisor somehow and has to get there in a safe way. What you can do is you can send what we call an @secret request structure or an @secret request control block. Well, actually, you would send it to the secure guest, and the secure guest then would call an instruction to forward this request to the ultravisor. And this instruction is not interceptable, so it would go right into the firmware without being intercepted by the hypervisor. This structure is ASGCM encrypted, so it has a confidential part that is encrypted and a additional data part which is only integrity protected. The association secret is of course in the encrypted part, its ID is in the open part. There's another secret in the encrypted part that I talk later about. Request contains a measurement of the image, so it can only be used with specific images. There's other data that I will talk later about, and it contains so-called key slots. The key slots contain the request protection key, the key used to do the AES-GCM encryption of the whole structure, and they are themselves encrypted with secrets that are specific to the target hosts. So that can only be opened by specific target hosts. They are built, of course, with the help of the public host key. Okay, so Let's look at the scenario. The owner of the guest that wants to use an HSM would build such a request. We have tooling to build these requests. We look at these later. And he would have a policy in the guest associating master key verification patterns or other configuration data of the HSM with the ID of the association secret. That request is sent to the guest. The guest would submit it to the ultravisor. The ultravisor, if there's a key slot for that machine, will be able to unpack the request, and then the ultravisor has this secret together with the ID. In the next step, the guest would bind the HSM. Then on the bound HSM, it would request the configuration data, for example, the master key verification pattern, and checking the policy if what he gets back and the ID that he just stored, the association secret that he just stored match, then he can issue the association request. And if the guest is paranoid, he checks the master key verification pattern again. Okay, so wide, so good. Is anybody afraid of you? You should, because we have introduced something that we trust. The add secret request containing the association secret. How do we know that on the weight between here and here, the right association secret is used? So we must make sure that the association secret requests are not misused. And there are essentially two types of misuses. One is that someone steals this association secret request and uses it for a different guest. And the second misuse could be someone intercepts the request and replaces it by a request, association secret, adding request of the attacker. And then we talk possibly to a system that is protected by something that the attacker can mimic. Okay, and that is, well, the part that cost me a few nights to come up with solutions for. So there are a few safeguards to disable misuses of these add secret requests. And the safeguards depend on the use cases. And there are two major classes of use cases to me for confidential computing, and the second class has two subclasses. So class number one of use case is the owner of the secure execution guest generates a secure execution guest and personalizes it for his or her own use. So, for example, the image has already a decrypt key, it has already an SSH key. That is possible with secure execution for Linux on Z because we have encrypted images. Otherwise, you couldn't just put such secrets into an image. That is the use case that is green. The other two use cases are that the tenant, the cloud client, takes an image from an ISV. He knows the image is a good one, it has been checked, he knows the measurements of the image, all that is fine, but it's the same image for all clients of that vendor. That image may or may not contain a secret of the vendor, but it does not contain a secret of the tenant, at least not when it's deployed. And now we can consider two deployment schemes. Deployment scheme number one, at start of the secure guest, all the data that makes up the guest, including the data used to personalize the guest. Personalizing a guest is the step of making a generic image, a generic guest, turning it into a guest that belongs to a particular tenant. Typically, a minimum is insert a tenant secret into the guest. That makes the personalization. So subcase 1, all the data to start the guest and to personalize the guest is available before the guest is booted. The second second subcase is the case where the guest is booted and then the personalization data can get created and gets delivered. That makes a big difference. Okay, let's look at the safeguards. First of all, the secret requests are bound to the image. So they have the image measurements in this secret request structure. Then I mentioned the second secret that is inside the encrypted part, the extension secret. All secret requests, you may have more than one, must agree on that secret. So that way you make sure that all the secret requests that you add to the guest come from the same origin, from namely that subject that knows the extension secret. Okay, now if you have a guest that is personalized to begin with, then there is another secret inside the metadata of that guest that you can bind the extension secret to, making sure that the secret request only works with that very image. And all the image instances that you started, they belong to the owner of to the creator of the image. Good. Well, it looks like, even though that's nice and secure and everything, the industry wants something different. They like these generic images more. If the image may be started and as part of an interactive attestation process, the personalization takes place, then with our attestation function, which among others gives you a configuration unique ID, so a unique ID of a guest image, you can use this unique ID, put it inside your request, and then the request is bound to that very instance of that secure guest, that running secure guest. But that can only be done once the guest has been started. So that may not fit all purposes. If it's your purpose, it's a secure thing to do. Now, if you want to provide your configuration data right to begin with, like an IBM product, HyperProtect does this, they have something called a contract that contains all the data that gets read at boot time, and in order to personalize the guest, and you want the association secret to be part of that contract, then you want to generate the secret request before this guest has been started. So you cannot use something like the unique ID of this started guest. And therefore you can use user data. The user data allows you to put some signature into the additional signature into the secret request. I will get into that later. Next slide. And last but not least, during the lifetime of a guest, the guest gets more and more insecure. Yes, at the very beginning, the guest is very constrained, doesn't have any I/O, it just does what it was supposed to do, and then the I/O opens, and all of a sudden you are subject to whatever network attacks. So there is a means to tell the ultravisor at one point in time, do no longer accept secrets, new secrets, which is probably it's a good thing to do this in the first period of your boot process at some time when you start opening, say, SSH, for example, for the first time, or another TLS connection to the outside. So what you can do with this signature is you can actually, the owner of the @secret request can actually sign the request. That would be almost everything of the request. He cannot sign the request structure tag because that is computed at the very end. But he can sign all other data with exception of the signature itself. And if the contract data that is used and that is used to personalize the guest contains a certificate. If you want, you can also put the hash of the certificate in that field that is reserved for this. To verify the signature, then the guest code can be such that it only submits a secret request to the ultravisor of which the signature can be verified. And given that the guest code belongs, should belong to the guest image, so to the init RD typically, and therefore has been measured, and meaning that the init ID cannot easily or cannot be tampered with, you are sure that this test is actually performed. As soon as you think the guest is so open that you can no longer trust that code to submit something to the ultravisor, you should better lock the ultravisor to no longer accept further @secret requests. Okay, it has been implemented in Linux. So we have a new device driver to talk to the ultravisor. We have our crypto device driver has been extended to deal with bindings and associations. There are toolings where you can look at the status and you can actually change the status. The image, we have a tool to generate images, images for secure execution, that is scan-plot image, and we have new tools to add the secret request. That is, by the way, these new tools are written in Rust. You can create a secret request on any platform. You can add the request, of course, only on an IBM Z platform because that part is Z-specific. There is a sub-command to verify the user data if you happen to have this user data, and an option to lock the ultravisor for using further secrets. Given that the association of, association secret with the right HSM is a little bit tricky. We have also a configuration tool that allows you to write policies that do these associations. And this is just a sample of such a policy where you have a name that can be turned into the idea of the association secret, and here is, this hex string is the master key verification pattern, and the tool would then use, look for an HSM that happens to have the right master key verification pattern in order to associate the right association secret. And that's where I'm at the end of my talk. So it's non-trivial to use HSMs in a virtualized environment, unless you have a confidential computing environment with similar techniques that I described this time. And well, on IBM Z, we have managed to make this happen for our crypto adapters. Are there any questions? in a way, what I well, first of all, our firmware cannot connect to an arbitrary HSM. I think it would be sufficient to do that association at the point where I said we check the master key verification pattern. So what HSM typically do have, you install certificates that you can request. So there are other means than just the master key verification pattern where the HSM can identify itself.
You said that you have different key slots for the new hosts, and what process should be like when you want to add a new host to already encrypted images?
Something that's not there yet, or you have to generate a new secure execution header. You do not have to generate the image itself, just the header with an additional slot. So you can, well, the number of slots is just constrained by the size of the header, which is currently, I think, 8 kilobytes. So it's quite a few slots that you can put down. But yes, we know it's not really great if the cloud shrinks and extends dynamically. We are aware of that.
Is the ultravisor code open or available somewhere?
Which code is open?
The ultravisor one.
Unfortunately not.
Do you have
I'm not in a company that, at least for its hardware, is renowned to be very open. We are neither ARM nor RISC-V in that respect.
And maybe because the ultravisor, it's only firmware, so it's only source code, right? It's not tied, or is it tied to a very specific, for example, the Crypto Express support, that is hardware. So, okay, I understand that it's intellectual property and all this sort of stuff. But the whole thing is that with the ultravisor, I mean, do you know if there is some plan to open source it, because it can really be useful for the whole community?
I know that, and I would even be in favor of it personally, but I can't make you any hope. Too much hope there, I'm sorry.
Oh, no worries, it's okay. I understand that it does not depend on you only, so.
So what is the form factor of this adapter? Is it a PCIe?
Yes, PCIe.
And
But what the interface the operating system sees is not PCIe. That is the 3 instructions that are architected in our instruction set.
What does level 4 certified means?
Level 4, okay. This is the scrutinity with that the FIPS certification is performed with. So it essentially means that we are tamper responding, that any attack on the HSM hardware can be detected, and not only detected, but in such a case, the secrets in the HSM will be destroyed. So if there's a coil around it, if you think you have to penetrate this coil, or if you want to X-ray it, or if you want to freeze or heat it or whatever, these kind of things get detected and it gets destroyed. Even if you rip it off the machine, I'm not an electrical engineer, but I trust our electrical engineers that they made it, that then some electrical fluctuations make the adapter realize I'm being ripped off and that it is destroying the secret unless it has been configured to be unplugged. In case you want to transport, you want to rightly transport it from one place to another. question. Thank you.
Has anyone else tried to use a clicker? Does it work? Anyone knows? Okay. It's fine. All right, can I just start, or do we need a break after the last talk? Okay. All right, sure. Sounds good. All right, hi, my name is Andrei, and welcome to my talk about the Slab allocator, or specifically about the internals of the Slab allocator that would be relevant to Linux kernel exploit developers, and probably also to people who want to just read and understand exploitation write-ups to maybe add some kind of mitigation to the kernel to make it harder to exploit. So I do read quite a lot of write-ups or other resources about the Linux kernel, and what I noticed is that people who write write-ups for exploits, they don't go deep into explaining the internals of the allocator to explain how they shape slab memory to make the exploitation of a slab corruption possible. And then we do have some articles that explain the internals of the slab allocator, but the problem is that those don't cover how the slab internals are connected to the actual shaping of slab memory in exploits. So what I wanted to do is I wanted to cover the gap that we have and both explain the basic internals of the allocator and then based on those internals explain why common strategies of slab shaping work in exploits. There is a bit of a problem with this talk as technically I need 2 hours to go through all the slides. But what we're going to do is, first of all, I'm going to skip some of the introduction chapters that I have. So instead, well, first of all, probably everyone here, since this is a Linux kernel specific conference, everyone has at least a little bit of an idea about how the kernel dynamic memory management works. So people probably know the difference between the page allocator and the slab allocator, for example. And so I'm going to skip that part. And if you're watching this in the recording, you want to go to the slides and probably check out the slides first for those skip parts. And the second part that I'm going to partially skip is the description of the slab allocator API. So if you know that there is a kmalloc function that allocates memory, keyfree function that frees memory, and then you know the difference between like common kmalloc caches versus caches that are created for specific types, then you know everything that I'm going to skip. So yeah. I do want to cover one specific detail about the idea of the slab allocator because we're going to need it when we're going to be discussing specific memory corruption that happen within slab allocator. And I want to explain where the word slab comes from. So the slab allocator, it manages memory in these big chunks called slabs, and these chunks are allocated from page alloc, so from the page allocator. The slab allocator allocates these big slabs and it splits them into smaller object slots. And whenever a user being the kernel, requests a certain amount of memory to be allocated, it gets allocated from one of these object slots in one of the slabs. So technically inside of the kernel you have many different caches. Each cache has its own slabs, so slabs are split into the objects of the same size. And when you call kmalloc, you get a pointer to one of these object slots. So that's like the core idea that we need to know before we proceed. And the next thing I want to mention is that technically the slab allocator does not exist. There are 3 different slab allocators within the kernel, or rather in the upstream kernel right now there is only sloop left, everything else was removed, but when you're writing an exploit, maybe you're targeting an older kernel and you might have a different flavor of the allocator. So all of these 3 flavors, sloop, slab, and slop, they follow the same API, but they have different implementation. But for years, the sloop allocator was the default, so this is what we're going to focus on. All right, let's talk a bit about what kind of memory corruptions we might have with the slab allocator. So the memory corruptions that happen, those are the typical bugs that you might have with any kind of a dynamic memory allocator. You might have out-of-bounds accesses, use-after-free accesses, memory being freed twice, invalid pointers being freed, and stuff like that. Within the talk, we're going to focus on the out-of-bounds use-after-free bugs just because there is not enough time to cover everything. But I do have some notes about double freeze at the end, and invalid freeze we're just going not to discuss. Let's look at a few basic scenarios how these memory corruptions can happen. So we do know that we have these slabs which have object slots, and let's assume that within one slot we have a vulnerable object. So throughout this presentation, whenever I'm going to be saying the word vulnerable object, that means that this is a specific allocation that is affected by some kind of vulnerability. And here we assume that our vulnerability is an out-of-bounds access from within the object. So since the object is located within a slab, it might be that the next slot that follows this object on the slab is free. So when we have an out-of-bounds access, this access lands in a free slot, and the sloop allocator does store some metadata within free slots, so it might be that the access corrupts the metadata or leaks the metadata to user space, for example. In a different scenario, it might be that another object is allocated in the next slot, and in this case, the corruption is happening, so the access lands in an allocated object of a different kind. For use-after-free, similar things can happen. So first of all, we can have a use-after-free scenario where memory is freed, so memory is allocated, so a specific object is allocated via keymalloc, then it's freed via keyfree, and then it's accessed via a use-after-free reference. So we assume that since we have a use-after-free bug in the kernel, after the pointer was freed, the kernel still holds on a reference to this pointer, so it can still access it, and this is the use-after-free bug by itself. And in this case, we're accessing free slot, so in case nothing else was allocated in the same slot, we access a free slot, the kernel accesses free slot, but it might be that the kernel allocates another object in the same slot, and in this case, the access lands in another object. So these are just typical scenarios that might happen. And a Linux kernel exploit that uses a slab bug, what it wants to do, it wants to use the slab memory corruption to do either one of 2 things. So either it wants to attack the metadata that is stored within the free slot. It is tricky with the sloop allocator due to mitigation, but it is still possible. Or maybe it wants to corrupt some other object. So you can imagine that if we have another object that contains, for example, a function pointer, and we're able to override that function pointer via out-of-bounds use-after-free, and then make the kernel trigger that function pointer, we might be able to hijack the control flow of the kernel execution and thus escalate privileges, as an example. And this is a much easier approach. So for the most part of the talk, we're going to be discussing the second approach of corrupting a different object. And I'm going to explain why the first approach is tricky with the modern kernels. So for any slab memory corruption, you would need 3 things. First of all, you would need a kernel bug that triggers out of bounds and use-after-free. And we're not going to be discussing any specific kernel bugs throughout the talk. We're just going to assume we have one. The second thing that you need is some kind of a target object that you want to corrupt or maybe leak. And this is the part that is also out of scope of the discussion. There are many target objects that are commonly used in Linux kernel exploits. So to find out about those, you just there are some lists of objects, there are write-ups, so you can check out those. So this part we will also leave out of scope, and we're going to assume that we chose some kind of an object that we can corrupt, some kind of a kernel allocation with a function pointer, some other pointer that we can override. But the part that we're going to focus on is how to shape slab memory to exploit out of bounds and use after free. So for out of bounds, we'll need to figure out how to put the vulnerable and the target object next to each other. And for use after free, we'll need to figure out how to put target object into a slot that is referenced by use after free reference. And this is going to be the focus of the talk. So of course, to understand how to shape slab memory for exploiting slab bugs, we need to understand the internals of the allocator. So let's start with that. We are going to have some additional constraints on the internals of the allocator. So first of all, I'm going to be targeting the latest long-term kernel 6.6. And the reason is that this loop allocator, it evolves and things change. For example, in 6.8, there's already been some changes, and I'm going to reference some of those throughout the slides. This is the first thing. Then the loop allocator has a lot of different configuration options, and we're going to assume the most default one. For example, we have the per CPU partial slabs enabled. We have the loop debug functionality disabled. It's typically disabled on a production kernel. We're not using the tiny version of the allocator and stuff like that. So some of the things we're also going to leave out of scope, like details about the locking, because we're not really discussing the performance of the allocator. We just want to understand how it works for Linux kernel exploits. And then we're also going to be focusing on a single cache. So we're going to exclude all of the cross-cache corruptions, different kinds of cache interactions like cache merging. So just focus on the basics. All right, let's start with the first thing, is discussing the struct KMM cache. So within this loop allocator, each cache has a corresponding structure called KMM cache. And if you check out the definition of the structure, you're going to see that there is quite a lot of different fields within the structure. Some of those might kind of be understandable. So for example, we have the cache name here as a pointer to the name. Each in the kernel, we have different caches like kmalloc caches. So kmalloc caches are going to have kmalloc dash some number as the name. And then, for example, we have the variable that specifies the object size. So this is the size of the objects that are going to be allocated within the slabs for this particular cache. The rest of the fields we're going to discuss one by one, the ones that are relevant to us. So the first field that I want to discuss is a pointer to a KMM cache CPU structure. This is a per CPU pointer, which means there is an instance of this pointer for each CPU core that you have on the system. And as a result, there is an instance for this KMM cache CPU structure for each CPU that we have on the system. And this KMM cache CPU structure holds some data that is tied to a specific CPU within the system, and the reason the loop allocator does that is for performance reasons. Usually this is why you use per CPU variables. You might have many CPUs. You want to avoid different CPUs taking locks to access some common, some shared data. So as a result, you cache data per CPU. Then we have this other pointer or an array of pointers to KMM cache node structure. And there is one instance of this structure for each non-uniform memory access node that you have on the system. So this is also done for performance reasons. You can imagine you might have a computer with different memory banks, with different access properties. So within this talk, we're going to assume that we only have a single NUMA node. Discussing multiple nodes is just out of scope. And for the CPU, for now, we're also going to assume that we have only one CPU. The reason is because usually during slab shaping, you want to avoid different kinds of cross-CPU interactions. As a result, you pin your exploit process to a single CPU, and you only interact with this loop state for a single CPU. But in some cases, other CPUs might come in and might be relevant, so we're going to discuss those a bit later. So for now, just one NUMA node and one CPU. So each of those structures contain pointers to slab structures. So remember, we already discussed what a slab is. Slab is an allocation that holds many objects. And we have some slabs that are per CPU, and then we have some slabs that are per node. So for each CPU, we might have some slabs that are tied to the CPU, and for each node, we might have some slabs that are tied to each node. So here you can notice instead of using a pointer to a slab, here they use a double linked list, but it doesn't matter. This list still contains a list of slabs. Before I explain what is the difference between this slab pointer and partial pointer and what is the difference between CPU slabs and node slabs, let's study the struct slab in a bit more detail. And this is the next part. So for each slab that we have inside of the Linux kernel memory, we have a corresponding slab structure. And this structure is aliased with the page structure. So page structure is a structure for each physical page that you have on the system, there is a corresponding page structure. Depending on whether this physical page is a normal physical page and maybe it belongs to one of the slabs, the layout of the structure is different, and this is a simplified layout in the case where this page belongs to a slab. And well, the one of the fields is kind of obvious here. For example, there is a pointer to the cache that this slab belongs to. The rest of the fields we're going to discuss. Then remember that each slab, of course, has backing memory. This is the memory that's allocated from pagealloc, and this is the memory that contains object slots. Some of those slots can be allocated, some of those slots can be free, so depending on how long ago this slab was created, of course, since this loop allocator manages the memory in this slot, in this slab, slots get allocated and freed all the time. The size of the allocation that is used for slabs is calculated based on object size, and here throughout the slides I'm going to have links to the specific parts of the Slab source code that do different kinds of calculations and actions, so if you're studying the slides on your own, you might want to check out those links. And of course, a slab can span up across multiple pages, can be 1 page, 2 page, and bigger slabs. To find out the size of the slab for a specific cache, which might be important when you're writing an exploit, you can use the proc slab info file, which shows you different information about the cache. So here, for example, it shows you the object size that is used within each cache, the number of objects that you have per slab, and the number of pages that you have per slab. So for smaller caches, the number of pages that you have per slab is typically just 1 page, but for caches that manage big objects, for example, kmalloc 8K manages objects of 8 kilobytes, and it has 8 pages per slab. Just slabs are bigger, which makes sense. Each slab has a field which is a free list pointer. A free list pointer is a pointer to the first free object within the slab. And first here means this is the first object that is going to be allocated from a specific slab. And as an initial note, there is no pointer to the beginning of the page allocation from within the struct slab. And the reason for that is because there is no need for it. Struct slab is essentially struct page. So you can just use there are some kernel macros that allow you to calculate the address that corresponds to a page allocation based on the address of the corresponding page structure. All of the free slots within the slabs are linked via a free list. So we have this free list pointer that points to the first free slot within the slab, and this memory is technically free, which means no kernel user, like the Linux kernel does not use it. Well, the Linux kernel external to the Slab allocator does not use it, which means that the Slab allocator can store any kind of metadata it wants within the free slot. And the only metadata that the Slab allocator stores within free slots in the configuration that we assume is a free list pointer to the next free object. So inside of this first free slot, we're going to have a pointer to the next free slot, inside of that free slot, pointer to the next one, and once the free slots within the slab run out, the last pointer is null. And this is how the Slab allocator links all of the free slots within each slab. So when we are allocating objects from this slab, when the Slab allocator decides to allocate objects from this slab, it's going to allocate them from the front of the list and also free them to the front of the list. Let's talk about how the free list pointer is stored within the free slot. So it is stored near the middle of the slot, and the way the address of the free list pointer is calculated, essentially they take the address of the object and add the object size divided by 2 and align it to 8 bytes. So essentially this is around the middle, and the reason this is done, it used to be that the free list pointer was stored at the beginning of the object slot, but then if you have a 1 byte memory corruption, like a 1 byte out of bounds bug, you can overwrite one of the bytes of the free list pointer and maybe get a stronger memory corruption based on that. So this is why the free list pointer was moved into the middle of the slot. In addition to that, the free list pointer is hashed, so this is how the hashing happens. The original value of the free list pointer is XORed with the per cache random value, which is generated when the cache is created. And then in addition, it's XORed on something that's based on the address of the slot itself. So unless This was also done to make it hard to fake those free list pointers in Slab exploits. You can imagine that if you can override the memory within the free slot, you might be able to fake the free list pointer if it's just stored there as is. But if it's hashed, you will need to first leak this per cache random value and then leak the address of the slot. So it's still possible, it's just hard. And as a result of these two things, people don't usually target this metadata that's stored within the free slot. So it used to be very common, not anymore. Nowadays, all Slab exploits tend to target the allocation of another object type that is stored within the same slot just because it's easier. So when a new slab is created, all of the slots within the slab are put onto the free list in random order. So it used to be that all of the slots would be put right one after another, and then it would be very easy to shape memory for out of bounds. You just allocate vulnerable, allocate target, and then get placed next to each other. Not the case anymore. Now you don't know the order of the free list slots on a new slab. So as a result, it's very unlikely if you just allocate two objects, then it's very unlikely, even if they belong to the same slab, it's very unlikely that they're going to be placed next to each other. And for full slabs, once all the objects are allocated, the free list pointer within the slab is just null. One last piece of knowledge that we need about the struct slab is that multiple slabs can be linked with each other on a list. And there are two different ways that multiple slabs can be linked. So first, there is a way to use a singly linked list, and this is what is used for per CPU lists. We're going to discuss that a bit later. So there is a pointer to struct slab within the slab structure, which is called next. And then if you have one slab, you can use the next pointer to point to another one, next to another one, and so on until you have the last one where you pointed to null. And in addition, there is the slabs integer field that shows how many slabs we have on the list, including the current one. This is one of the ways that is used, and this is a single linked list. And then they also use the double linked list. This is used for per node slabs. And here we just have a list head structure, so multiple slabs can be linked on a double linked list via this list head. Two different ways multiple slabs can be linked. Okay, as a summary about the slab structure, each slab has its own struct slab. Each slab has its own backing memory allocated from pagealloc. Each slab has one free list, which contains the free slot within the slab, and the free list pointers are stored within the slots, the free slots themselves. Faking free list pointers is hard. As a result, we're going to be mostly discussing faking or overwriting other objects. And then multiple slabs can be linked together. Just know that we have two different ways to link them that are used for per CPU versus per node slabs. All right, let's go back to discussing KMM cache structure. This is where we left things off, that we discussed we have this per CPU state, we have this per node state, and for per CPU state we have multiple slabs, for per node state we have multiple slabs. Let's discuss these slabs one by one. So first, per CPU slabs are the slabs that are bound to a specific CPU. And they also, before 6.8, they also used to be called frozen slabs. This is a particular detail of the implementation, so I'm not going to be calling them frozen slabs. Just know that these are the slabs that are bound to a specific CPU, which means that if a specific CPU are going to start allocating objects from this cache, allocations are going to come from these per CPU slabs first. That's the idea. And this is done, for performance reasons. We can cache some slabs per CPU, which means you wouldn't need, the loop allocator does not need to take expensive locks to access them. And then, in addition, this loop allocator has this per node slabs. And these kind of compared to the per CPU slabs, this is a global list of slabs. So let's consider the case where we have only a single node. So we have multiple CPUs, each with its own set of slabs. And then we have those global slabs, which belong to the only memory node that we have. And note, those slabs are not bound to any CPU yet, but they might become bound, they might be moved into this per CPU list at some point later. But they still belong to the cache and still might contain free slots. I mean, they are still slabs with the objects from the cache. They might contain allocated slots, free slots, and yeah. Let's discuss those two. So when you look at the per CPU slabs that you have, you will see that we have two different pointers. The first pointer is a pointer that's called slab. I call this one active slab. And the other is actually going to be a list of pointers for partial slabs. Let's talk about the active slab first. So one of the per CPU slabs that you have for each CPU is designated as active. And active is the word that I use to describe the slab, but if you check out the Sloop allocator source code, you will see that they call the slab the CPU slab. I think it's a bit confusing when you have the CPU slab and other CPU slabs, so instead I use the word active slab for the active slab, and the other slabs I'm going to call per CPU partial slab just to avoid confusion. And this is also what most external write-ups do. If you're reading some exploitation write-ups about the Sloop allocator, it's going to use the keyword active. So active slab has a unique property is that allocations that happen on this CPU from this cache happen from this slab first. And that's the idea. We have one single slab which is used first to serve the allocations. One additional unique property about this slab is it has two different free lists within it. So remember we already discussed, so each struct slab has a pointer to a free list and it contains free object slots that belong to this slab. But for the per CPU slab, there is actually an additional free list from the KMM cache CPU structure, which also points to the object slots within the active slab. This is the part that's usually missed by most like security-related write-ups about Sloop. And it's not particularly useful for exploiting basic memory corruptions, but at the point when you have multiple CPUs working against each other and you have some kind of a racy slab shaping technique, this is the fact that might be relevant. So this is how it works. This is, let's imagine we have this backing memory for the active slab. We have some free slots within it. And the two free lists, they link slots with the free slots within the slab, but they don't intersect within each other. So we have this lockless per CPU free list that is a field of the KMM cache CPU structure. And lockless, it's in the sense that when the current CPU wants to do some kind of operations with the slab, it doesn't have to take any locks. So it just uses this lockless per CPU free list to free object slots onto the slab or allocate object slots from the slab. And the per active slab free list, it is used in cases when other CPUs want to free objects that belong to the slab. So you can imagine a case when we have an active slab for a specific CPU, but the address of one of these objects on the slab, it's used by another CPU to issue a key free against. It just key frees an address from the slab. So the result, in this case, the object is not going to be put on the lockless free list, it's going to be put on the per slab free list, and the Sloop allocator will need to take the per slab lock, but this is out of scope of our discussion. So yeah, just know, two different free lists. We have a lockless free list for the current CPU usage, and we have another free list that's used by other CPUs. And the slots on these two free lists, they don't intersect. So these are completely two separate free lists, which means we're going to have two different slots within the slab that end with a null pointer, for example. All right, this was the details about the active slab. Now let's talk about the partial slabs. So partial slabs, this second field that we have within KMM cache CPU structure that's called partial, this is a pointer to a list of partial slabs. So partial here means that these slabs have free slots. So there is at least one free slot within each slab. They can be fully free, but we definitely have at least one free slot. Of course, each of the partial per CPU slabs has its own backing memory, and each of the partial per CPU slabs has only a single free list. So in the active slab, it was more complicated. We had two different free lists. In this case, it's fairly simple, just the per slab free list with the free slots within the slab. And these are the slabs that are going to be used for allocations after the active slab. I will discuss this in more detail in the second part when we're going to be discussing the allocation algorithm. So for now, just know we have the active slab that's used first, the per CPU slabs that are bound to the CPU, but they're not used before the active slab gets full. And the final part is that we have this global list of per node partial slabs. So they're also partial, which means they also have at least one free slot within them each. And they also have backing memory, they also have just one free list, and they're going to be used for allocations after we run out of all the per CPU slabs. But again, more details about this later. There are some limits about how large these lists can be. So first, for the per CPU slabs, for the per CPU partial slabs, there is a maximum number that can be kept on the per CPU list. And this number is described by this CPU partial slabs field of the KMM cache structure. And Unfortunately, there is no way to find out this limit from user space. It's just not exposed to user space. Instead, the slope allocator exposes a slightly different number, CPU partial, but this CPU partial slabs number is calculated based on CPU partial. So if you know CPU partial number, which you can get from the what they call sysfs file system, then you can calculate the maximum number of slabs that you might have on the per CPU list for a particular cache. And you do need to know this number for certain advanced slab shaping attacks. For example, that the cross-cache attacks, they abuse overflowing this per CPU partial slab list to execute the cross-cache attack. But I'll talk about this a little bit closer to the end. So for the per node list, we also have some kind of a limit, but it's not a hard limit. So instead, for the per CPU partial list, we had the limit of the maximum number of slabs. Here we have the number of slabs that the slab allocator tries to keep on the per node list. So this number is exposed. This is called mean partial number, and the slope allocator tries to keep at least mean partial slabs on the per node list always. So even if the slabs get fully free, even there are no allocated object slots, so normally the slope allocator would want to free those slabs back to the page allocator because it doesn't need that memory anymore. But for per node slabs, they're an exception. So if we have at least mean partial slabs, if we don't have yet mean partial slabs on the list, then even if you have empty slabs here on the per node list, the slope allocator is just going to keep them around. And here I have a table with the numbers for k-malloc caches. I'm going to skip those because this is just for reference, maybe for those who are writing kernel exploits. So slab of each type can be fully free. We can have a fully free active slab. We can have a fully free slab on a per CPU partial list, and we can have a fully free per node slab. And some of the exploits rely on this behavior that some of the slabs are kept fully free. And for full slabs, they're just not tracked. So the moment the last free object slot within a slab is allocated, at this point the slope allocator forgets a reference to the slab and it doesn't keep it on any list. So the moment the slope allocator gains a pointer to the slab again is when one of the allocated slots on the slab gets freed. At this point, it just uses vert to slab to calculate the address of the slab structure, and then it puts it back onto one of the partial lists. So a bit more detail about the namings. I already mentioned about the active slab, so I use a slightly different naming scheme for naming the slabs. Inside of the kernel code, you will find either the CPU slab or just CPU slab for the active slab. For the per CPU partial slabs, they're named more or less similarly in the source code and my presentation. They're called per CPU partial slabs, so just CPU partial slabs. And another difference that we have is here. So these per node partial slabs, I specifically call them per node, but the Linux kernel source code sometimes omits this per node name and instead just says partial slabs. So if you're reading the source code and you see a reference to partial slab, without specifying whether it's per CPU and per node, it's going to be the per node slab. All right, and as a summary, this is the layout that we have. We have KMM cache with one KMM cache CPU for each CPU. The KMM cache CPU has two different types of slab. We have the active slab with two different free lists. Allocation happened from here first. We have a list of per CPU partial slabs. Each has just a single free list. And then we have the per node state with a list of per node slabs that each has backing memory and a single free list. And of course, the full slabs are just not tracked, so they exist somewhere, but the slope allocator does not keep them on any list. So this is the summary of the layout that we have within the loop. Now, before we talk about our first slab shaping exploit, let's talk about how the allocation happen. How the allocations happen. I already briefly mentioned that we have active slab first, then per CPU slabs, then per node slabs. Let's put it onto the slides. So within the slope allocator, we have 5 different tiers of allocation process. Also not an official term, so I just call them tiers. So the first tier is allocating from the lockless free list, second tier from the per active slab free list, then we have per CPU slabs, per node slabs, and finally we can create a new active slab. Let's go through them part by part. So the first step is, let's say we're trying to allocate a specific CPU is trying to allocate an object from a specific cache. The first case is the per CPU partial list, the lockless, is the lockless per CPU free list empty? If the lockless per CPU free list is not empty, then the slope allocator just allocates the first object on that free list and we're done. If it happens that this lockless free list is empty, then we go to step 2, we go to tier 2, allocating from the per active slab free list. So remember that within the active slab, we do have two different free lists, the lockless free list and the per slab free list. And this tier 2 is when the lockless free list is empty, but the per slab free list is not empty. In this case, what the slope allocator is going to do, it's going to move all the objects from the per active slab free list into the lockless free list. For that, it will have to take a lock, of course, and release the lock. And at this point, we can go back to tier 1, which is allocating from the lockless free list. So a bit more complicated for the active slab because we have two different free lists, but we allocate from the lockless, try to allocate from the lockless free list first, and then from the free list that requires locking. And if it happens that both of these free lists are empty, or it might happen that we just don't have a pointer to active slab, it depends on the exact branch that is taken within the allocator source code, we just go to tier 3. Tier 3 is allocating from this per CPU partial slab. So we assume we don't have an active slab yet, and we are going to use the per CPU partial slabs. And the way it works is that the slope allocator just takes the first slab from the per CPU partial list and then assigns it as the active. Fairly simple. And at this point, we can go to the previous step, allocating from the active slab. So take the first from the per CPU partial list and use that. If we don't have any per CPU partial slabs, we go to tier 4, which is allocating from a per node slab. So in this case, a slightly more complicated thing happens. So first of all, we do take also the first slab on the per node list and assign it as active. But in addition, the slope allocator is going to move some of the per node slabs to the per CPU list. So the idea here is that since we run out all of the allocations within the per CPU slabs, most likely this particular CPU is trying to allocate a lot of objects. So it just makes sense to put some slabs onto these per CPU lists so that the CPU can allocate more of them in the foreseeable future. So the first step, designate the first per node slab as active, and the second step is move some of the per node slab to the per CPU list. And at this point, we can just go to allocating from active slab. So this is go to one of the previous steps. And the final case is when we don't have any slabs or any of the lists. In this case, the slope allocator just allocates a new active slab. So it goes to page alloc, asks for some pages, creates a free list for the slab in a random order, assigns it as the active slab, and at this point we can allocate an object from the slab. So 5 tiers: lockless free list, per active slab free list, per CPU partials, per nodes partials, and creating new slab. All right, this might be a lot of details, so let me explain the core things that we need to know before we can discuss the first exploitation primitive, that exploitation approach that we're going to discuss. So first, we do have many caches, and each cache has many slabs that store objects, some of those object slots. Some of those object slots can be free, some of those can have allocated objects from the previous kernel operation. Then we do have the separation between different types of slabs, and the allocation, they happen from the active slab first. And once the slots in the active slab get run out, we assign the slope allocator assigns a different slab as active. And if you think about step 2, so let's say we just start allocating many objects from the same cache on the same CPU. So we're going to fill the active slab, we're going to fill all the per CPU partial slabs and all the per node slabs, and at some point a new slab is going to be created with all slots empty, and it's going to be assigned as the active slab. So these are the 3 takeaways that we need to know. So let's discuss the first very simple case of shaping slab memory for out-of-bounds vulnerability. So this is a simple case in the sense that I assume here that we have 2 different system calls. One system call that allocates a vulnerable object, and another system call that triggers an out-of-bounds access from this object. This is not always the case with out-of-bounds vulnerabilities, but this is the case that we're looking at. So the trigger for the allocation and for the out-of-bounds access, they're separate. And remember that for the attack, we also need other things. We need like a target object. We assume that we have one. And this is the part we're going to discuss now, how to shape slab memory in such a way that the target object follows the vulnerable object in slab memory. So what can we do to achieve this? So for now, I'm just going to explain to you the algorithm that we're going to follow through, and then we're going to discuss why exactly it works. So the first step that most slab exploits do is they want to allocate many objects to get a new active slab. And the reason is they do it is because, well, essentially from the previous kernel operation, you do have the active slab, but it might have some allocations that are unrelated to your exploit. You want to get rid of those, you just want to create some kind of a predictable memory state. So as a result, you just allocate objects, and we're going to be using target objects to fill all the holes in existing slabs. I will discuss why that is a bit later. For now, just let's assume we use our target objects. And we are also assuming that we chose such a target object that can be allocated as many times as we want. Because we have arbitrary choice of target objects, we can do that. So let's discuss how many objects do we need to allocate to fill all the holes and get the active slab. So this is the slab memory that we might have before executing our slab shaping strategy. And these are the slots that we need to fill before a new active slab gets created. So how do we know how many holes we might have in a cache when our exploit starts running? And unfortunately, there is no way to find out the exact number, just because these numbers, they can be found out through the proc slab info file, but this file is just not accessible to unprivileged users. And we do assume that our exploit runs as an unprivileged user. And there is also no upper limit on the number of free slots that we might have. And the reason is that we do have a limit on the number of holes on the active slab. We do have a limit on the number of per CPU slabs, which means we have a number of limits on those free slots. But there is no limit on the number of slabs that can be on the per node list. As a result, there is no limit on the number of free slots or holes, how I call them, on all the slabs. So instead, what people do is they use one of two approaches. The first approach is try to estimate how many holes you might have. And the way this works, you just reproduce the environment. So we're assuming we're trying to attack some kind of a target server, let's say, with a certain environment. We reproduce that environment locally. We run the same kernel version. We try to run the same user space workload. We try to give it some uptime, and then see how many holes within the slabs you have on the local system. Because you can debug your local system, you can find it out easily. So I'm going to explain how exactly to get this number on the local system in the next slides. But the problem is that this number is not going to be accurate. Of course, a remote system might have a different number of holes. But this is already good enough as an estimate. It makes sense to take a bit more. Maybe we want to take twice more, 3 times more, 10 times more. But at least this gives you an idea of the order of magnitude of the number of holes that you might have in each specific cache. And there is an alternative which I will leave out of scope. This alternative is relying on timing side channels to figure out whether you allocate, to figure out the moment when you get a new active slab. And the idea is there, you just keep allocating objects and you keep measuring the time the syscall takes to execute to allocate a certain object. And the moment you see that the syscall took a while longer than before, probably this is the moment this loop allocator had to go to pagealloc to allocate a new active slab. And this is how you can kind of figure out through a side channel that you got a new active slab. I do have some links about this approach at the end, but I will leave this out of scope. So let's just discuss the simple approach. Let's assume we're just writing a simple proof of concept exploit, and let's see how we can get an estimate of the number of holes. So within the proc slab info file, for each cache that you have on the system, you have 2 numbers. The first number, active objects, this is the number of allocated slots within all slabs that you have for a cache. So each cache can have many slabs, and this is the number of allocated slots. The second number is the total number of all slots, counting both allocated and freed ones. There is a bit of a problem with these 2 numbers, is that for the slope allocator, they're not updated all the time, so they're not kept up to date. So if you check here, for example, for CredJar cache, these 2 numbers match, which is a very unlikely situation that all the holes, all the free slots within all the slabs that we have are filled. This is quite unlikely. So to find out the actual number of holes that you have in a slab, you have to force the slope allocator to update those numbers. There are a few ways you can do that, but one of them is you can shrink the cache. So there is a special shrink file which you can write into, and at this point the slope allocator will update these numbers. There is a bit of a problem with using specifically this approach, because as a result of shrinking, the slope allocator will also free all of the fully free slabs that it has for this cache. So the number of holes is actually going to be different after the shrinking than before the shrinking. But this is still good enough to get some kind of an idea of how many holes you might have. So here, for example, before the shrinking, the numbers were the same, and after the shrinking, we have about 1,000 objects of a difference. So in an exploit, maybe you want to allocate like 2,000, 3,000 objects to fill all the holes that you have in the KML32 cache. Okay, let's assume we filled all the holes, so let's assume we got a new active slab, and it's going to be partially filled with target object just because we kept allocating target objects. So once we got a new active slab, we don't know exactly the moment when we got active slab, because we don't know exactly the moment when we managed to plug all the holes. So the assumption is that we do have some target objects on active slab. Now we're going to use our syscall that allocates one vulnerable object. And of course, because the allocation happened from the active slab, the object is going to be allocated from the active slab 2. And it's going to be placed somewhere in the slab, we don't know where exactly. Step number 3 is we're going to fill this active slab with target objects. So we do know that the maximum number of objects per slab for a particular cache is a certain number. This is the opt per slab number. And we do know that we already have at least one object within the active slab, which is the vulnerable object. So we just allocate opt per slab -1 target objects on top. And the first few of them are going to be placed in the active slab. So the active slab is going to be filled. And then, of course, maybe a new active slab is going to be created and some of the target objects will spill there. But we don't care about that. The thing that we care about is that we fill our new, like old active slab with the target objects. And at this point, if we triggered out of bound access, it just happens that it lands in one of the target objects. So our slab shaping approach allowed us to create a new slab which has one vulnerable object, and all of the other object slots are taken by target objects. And as a result, it's very probable that the object that follows the vulnerable object is going to be the target object. And this is what we wanted to achieve. So let's discuss what is going to happen if we skip some of the steps. First, what's going to happen if we skip this step 1 when we allocate target object to plug the holes and get a new fresh active slab. So this could be the original state. We could have some original active slab before we started our slab shaping, and it has some allocated objects from the previous kernel operation. And it can happen that once we allocate a vulnerable object, it just gets placed before one of those previous kernel objects, and we fail to corrupt target because we end up corrupting some other kernel memory, which is bad. This is why we do this first step of filling the holes and creating a new active slab that only contains target objects. Then the question is, why do we specifically use target objects to fill the holes? What if we use some other type of object? Let's call them plug objects. So let's say we use these plug objects to get a new active slab, to fill all the holes and make the slope allocator get a new active slab. Some of those plug objects will end up on this new active slab. And at this point, if we allocate vulnerable object and it happens to be placed before this plug object, then we fail to overwrite target object, we overwrite our plug object instead. So this is why we use target object for plugs. The reason is because we have some objects allocated during step 1, we have some objects, then vulnerable object, and we have some target objects allocated during step 3. And the vulnerable object, it can be placed before an object from step 1 or before an object from step 3. So in both steps, we want to use target objects. There are some things that can go wrong. For example, it can happen that the vulnerable object is placed last on the slab. So a slab has a certain limit. If vulnerable object ends up last on the slab, then we fail to overwrite target. So as a result, slab shaping, there is no way to make slab shaping work in 100% of cases. Well, this particular problem can be resolved. It requires the page allocator level shaping, so you can just shape page allocator memory in such a way that this slab with the vulnerable object is followed by another slab that filled with target objects. And in this case, you can resolve this and get 100% of success chance with regard to the specific issue. But we'll leave it out of scope. So just know that there can be some problems. Another problem that might happen, so let's assume we have multiple CPUs and we start executing our slab shaping strategy. So it could happen that our exploit process gets migrated to a different CPU in between, like during the slab shaping execution. So this is a problem because once it's migrated to a different CPU, it starts using the active slab of that other CPU. And our slab shaping strategy fails because it relies on the fact that we use a specific active slab and the active slab does not change throughout slab shaping. Luckily for this particular problem, there is an easy way to solve that, is we can pin the exploit process to a specific CPU, and this can be done by an unprivileged user. So just call the shared set affinity syscall, and this problem is resolved. However, there is still a different problem, which is called preemption. So preemption is different from migration. Preemption, and when the task that's being executed on a certain CPU gets preempted by another task to be executed on the same CPU. And this is also a problem for us, because if our exploit process gets preempted in the middle of slab shaping, some other process that starts running on the same CPU, it might start using the same cache, so it might start using the same active slab within the cache, and it might allocate a free objects from that active slab. And this is a problem. And for dealing with preemption, unfortunately, there is no single perfect approach. There is just some ways you can kind of deal with that to get your slab shaping strategy work in most of the cases. So here I have some of the ideas. For example, it makes sense to minimize the time you spend on slab shaping, just because if you spend a lot of time, if you add some debug printfs in the middle of your slab shaping, probably not something that you want to do, because you increase the chance that your exploit process gets preempted, and this is a problem. If you have a choice, you can use a less noisy cache, which means you can try, let's say you have a vulnerability, and for that vulnerability you can choose object from which cache you're going to attack. Maybe KMalloc 128 or KMalloc 256. And then you can debug the kernel and see which of these two caches is used more frequently, and use the one that's used less frequently to avoid, so even your exploit process gets preempted, to avoid the case that these other tasks start allocating from the same cache. Then there are some other things, like getting a fresh scheduler time slice before executing the slab shaping, or checking whether you got preempted by reading this proc/self status file, or maybe timing side channels. But there is no one perfect solution. So slab shaping does not always work. You can make it work for certain. Like, you can make the success chance of slab shaping to be like 99.9% for certain types of exploits, but it's never going to be 100%. Okay, let's discuss a slightly more complicated case. And this is the case when we have a combined allocation and out-of-bounds trigger. So in the previous case, we had a separate syscall which allocated vulnerable object, and a separate one that triggered out-of-bounds. And in this case, we have one that both allocates an object and then immediately triggers out-of-bounds from the object. And with this second case, we cannot separate steps 2 and 3. So remember that in the previous approach, we had step 2 allocating vulnerable object, then step 3 fill the active slab with target objects, and only then we triggered out of bounds. With this combined approach, we cannot separate those will happen in the same step. So this is what we're going to do instead. I'm going to discuss two different approaches to this problem within the presentation. For now, this is going to be the allocation-only approach. So here we're going to be relying on the allocation primitive only. There is a different approach that you can use, but it relies on knowing how the frame works within the slope allocator. So we're going to move on to that later. So the allocation-only approach works like that. First, we do the same thing. We create a new active slab with target object. So at this point, we don't touch vulnerable object yet, so you can just allocate many targets to get a new active slab. And at this point, we're just directly going to use our alloc and out of bounds trigger to both allocate an object and trigger out of bounds without filling the active slab. And let's see what can happen. The first thing that can happen is that the slot that follows our vulnerable object is going to be a free slot. And let's say we have an out-of-bounds write primitive, and we're really worried about corrupting some critical kernel memory because this is going to crash the kernel. And the thing is that if our out-of-bounds write primitive does not write too much bytes out of bounds, we are going to be fine, because the only metadata that we have within a free slot is a free list pointer, but it starts somewhere in the middle of the object slot. So we can safely override the first few bytes, so depending on the size of the slot, maybe even more. And it's not going to cause any memory corruption. Of course, we're not going to corrupt the target objects. We're not going to override the target objects too, because it's just not here. But the important thing is that we're not going to crash the kernel, which means we can retry this slab shaping. Okay, we can retry this slab shaping approach and just do it all over again. So you can free all the objects and refill the holes and try it again. And at some point, hopefully, this is what we're going to get. It just will happen that our target object gets placed into the slot that follows the vulnerable object. So this happens. This target object is allocated from step 1 when we're filling the holes. And it just so happens that our exploit works. So this is fairly interesting because it used to be that free list pointer was stored in the beginning of the slot. And then when it was stored in the beginning of the slot, this type of thing wouldn't work. But now that the free list pointer is moved into the middle of the slot, it actually helps us with this particular exploitation approach, which is fairly interesting. So maybe, I don't know if it's a good idea to move it back into the beginning, because, well, some kind of a poison thing might work too. Yeah, but this is fairly interesting that it works now. All right, so far we covered the allocation process, we covered 2 different approaches to shape memory for out of bounds, and now let's talk about the freeing process so we can discuss use of the free too. And for the freeing process is fairly more complicated than the allocation process, so I'm going to split it in 2 parts. We definitely have enough time to go through the first part, and for the second part, well, we'll see. All right, so within the freeing process, we're going to look at a few different cases. So it depends which object is getting freed. And the first case for the first part we're going to look at is when the object that gets freed belongs to the active slab of the current CPU. So let's assume this is the object that gets freed, and it's freed by CPU A. And this is one of the slots of the active slab for the CPU number A. So we have Chemium Cache CPU for CPU A, we have the active slab, we have the backing memory, and this is the object that gets freed. And in this case, the freeing process works very simple. The object gets put on the lockless per CPU free list. So this is the free list that's used to allocate objects from this active slab on this CPU. And this is also the free list that's used to free the object. So it used to be here, now it's on the lockless free list. Very simple. And the only exploitation relevant outcome of this approach that is going to matter to us. Let's assume the following scenario. Let's assume we allocate one object via keymalloc, we free it. We allocate object of the same size again, we free it. We allocate another object of the same size again, we free it, allocate, and so on. All of these pointers are going to be pointing to the same object slot. Because when you allocate an object, it gets allocated from the active slab. When you free it, it gets put on a lockless active slab free list. When you allocate it, it gets allocated from the lockless free list. When you free it, it puts on the lockless free list, and so on. So all of these are the same object. Pointer 1 equals pointer 2 equals pointer 3. And this is very, very useful for us for exploiting use of the free bugs. So let's discuss the first case of exploiting use of the free. Let's assume we also have a simple use of the free vulnerability. So at this point we have 3 ioctls. We have 1 to allocate vulnerable object, 1 to free it, and 1 to access it. And this ioctl use of the free can be used after the object was freed. So I assume we can call ioctl alloc, ioctl free, and ioctl use of the free. And we want to shape slab memory to exploit this type of a memory corruption. So we want to override some kind of target object. Let's see how this works. So first we're going to allocate a vulnerable object. For this approach, you don't even need to plug holes, assuming you can directly allocate your vulnerable object via ioctl, via some kind of a syscall. No need to plug holes, you just allocate one object, it gets placed on the active slab because objects always get allocated from the active slab. Then you use ioctl free to free it back to the active slab, and of course it gets put onto the lockless per CPU free list. And we assume we still have some kind of a reference to this slot from within our vulnerable subsystem, just because we found the vulnerability and we have a use of the free reference. At this point, if we allocate target object, just one target object, it's going to be put onto the same slot just because the slot belongs to the lockless free list of the active slab. And here we have a target object and we have a use of the free reference that points to the target object. So at this point, if we trigger use of the free, we succeeded, we overwrite our target object with the use of the free access. Very simple. So unfortunately, this is not always how use of the free vulnerabilities work. In this case, we have a very nice vulnerability in the sense that we can allocate object and nothing else gets allocated. We can free it and nothing else gets freed and trigger use of the free. Sometimes it happens like that, but in a lot of cases it's way more complicated. It may be than when you allocate a vulnerable object, 10 more object, 100 more object get allocated in the same cache. And in this case, reclaiming that freed object slot is going to be more complicated. And this is going to be the part of the case too. So before we move on to case 2, let's discuss the rest of the freeing process. So far we only covered one part, if the object belongs to the active slab of the current CPU. Let's discuss the second case. The object that's being freed belongs to a slab that is not active slab for the current CPU, and this slab is not full. So we're going to have case number 2, when we have a slab that's not full, and case number 3, which is going to discuss when the slab is full. In those two cases, the slope allocator behaves differently. So let's say we have this other slab, and this can be maybe active slab of another CPU, or it may be one of the per CPU partial slabs for one of the CPUs, or maybe one of the per node partial slabs for one of the nodes. The first step in this case is also simple. The slab gets put onto the per slab free list. So for this other slab, regardless of what kind of slab it is, we always have this per slab free list, and the object slot that was just freed, it gets put first onto the free list. And then an additional thing that happens, and this is only applicable to per node slabs. So if it was a per node slab and the slab becomes fully free after this last object was freed from it, it might be that the slab is going to be freed directly to page allocator immediately. This happens when we already have enough slabs on the per node partial list. Remember, we had two limits. We had a limit on the per CPU partial slabs, which is a hard limit from above, and we have a kind of a limit on the per node list, and the slope allocator tries to maintain a certain number of per node slabs, but if it already has enough per node slabs and this slab gets free, then all of the object slots are free, then the slope allocator will just free it back to page allocator because it does not need that memory anymore, and this slab gets freed. So this does not apply to per CPU partial slabs, and it does not apply to active slabs. So only for per node slabs, it can be freed immediately during this case number 2, when we free a slot from a non-full slab. All right. Now a particular subcase of this case that we just discussed, it can happen that we have this object that belongs to a active slab of CPU number A, but the freeing happens by CPU number B, so by a different CPU. This is what's going to happen here is exactly what we just discussed. So the object is going to be put on the per slab free list for the active slab for that CPU number A. And the second step, this is not a per node slab, so it cannot be freed, so the second step is not applicable. Just as an example, that this works the same way for per CPU, for active slabs of other CPUs. All right, and let's discuss the last case, which is the most complicated one. If the object belongs to a full slab. So let's say we have some kind of full slab, we have a reference to it, and this is the object that gets freed. So the first step is the same. The object gets put on the per slab free list for the active slab. But at this point, the slab itself becomes a partial slab. So the slope allocator has to put it onto one of the lists. And the question is how exactly it happens. So what the slope allocator is going to do is going to try to put this slab on the per CPU partial list. The only problem is that we have a certain limit on the number of slabs that we might have on the per CPU partial list. And depending on whether this limit is exceeded or not, different things happen. So in the simple case, when the number of slabs that we have on the per CPU partial list is not going to be exceeded, so we have less than the limit. In this case, our new slab that was just full, that contains the object that's being freed, it's just going to be put first onto the per CPU partial list, well, and the rest slabs, the slabs that we had before will follow it. So nothing will happen with regards to those. So this is the simpler case. The more complicated case is when we already have a lot of slabs, so we already reached the limit on the number of per CPU partial slabs. In this case, the slope allocator will want to free up this list of per CPU partial slabs. And this is how it's going to do it. So it's going to go through that per CPU partial list slab by slab, and then it's going to move those slabs to per node list and to the end of the per node list. It's not particularly important for us for the exploitation strategies that we discussed, but it does move it to the end of the list. And then while it's moving those per CPU slabs into the per node list, it might free some of those back to the page allocator. So if we have a per CPU slab that is fully empty at this point, and we already have enough per node slabs, then at this point the per CPU slab will go back to the page allocator. And this is the particular behavior that's abused for cross-cache attacks. And we will leave this out of scope, but I'm going to have a reference to an article that describes how cross-cache works. And this is the behavior they rely on to free some of these per CPU partial slabs back to the page allocator to execute the cross-cache attack. So yeah, once the slabs are moved to the per node list, or maybe some of them get freed, at this point we have space on the per CPU partial list, and the slab to which the freed object belonged, it just gets put first on the partial list. So this case number 3 is the most complicated case that I discussed throughout the slides. So this is the case when we have a full slab and we free an object from the full slab. First object gets onto the free list, then the slope allocator tries to move it to per CPU list. If the per CPU list has space, it just gets put first on the per CPU list, the slab itself gets put. If the per CPU free list is already at the limit, the slope allocator is going to free it up by moving the slabs to the per node list, and then it's going to put the new slab first onto the list. This might be quite a few details to understand immediately, so it might be that those who want to figure out how this works will have to go through the slides once more. But here I'll give you the most important outcomes that we need to discuss the next strategies. So first, if we have an object that belongs to a per CPU partial slab and that object gets freed, the object itself, it goes on to the slab free list. So let me show a picture for this case. So if we have an object, maybe I don't have a picture here. Anyway, if we have an object in a partial slab, the object just gets moved to the free list of that slab and nothing else happens. If we have an object in a full slab, then the object does get put onto the free list for the slab, and the slab becomes the first per CPU partial slab. So if you go back here, you can see that in both cases, regardless of whether the per CPU partial list overflows or not, the new full slab always ends up first on the per CPU partial list. So in the case the partial list does not overflow, the slab that has a slot that was just freed, it ends up first on the per CPU partial list. In the case where the slab, the per CPU partial list did overflow, the slab which contains the object that was just freed, it still ends up first and the only slab on the per CPU partial list. So this is the second outcome that we need. The third one is for cross-cache attacks, so I'm going to skip it. All right, so let's discuss a more complicated case of shaping memory for use after free attack. So this is what we discussed before. This was the simple case when we were interacting with a lockless per CPU free list. We allocate vulnerable object, free vulnerable object. At this point, it's lost on the lockless per CPU free list. We can just allocate one target, and it's going to be placed again onto the same spot, and we're going to reclaim it. But in practice, it might happen that your use of the free vulnerability is different. And for example, it might happen that the use of the free reference you have to one of the slots. It's not the last slot on the per CPU lockless free list. It might be one of the slots on one of the CPU partial slabs, or maybe one of the slots on even on a per node slab. It really depends on the nature of the vulnerability that you have. And one specific case that I'm going to briefly discuss in when we're trying to upgrade out of bounds to use after free, it's going to be in a few slides. In the next few slides. And in this case, let's say what we're going to get is we're going to get a use after free reference to the first slot on the first per CPU partial slab. So the question is, if use after free reference points to here, but we still have an active slab, how would we reclaim that memory? And we're going to discuss that too. But first, let me explain what I meant by upgrading out of bounds to use after free. It's also one of the tricks that you can use with slab exploits, and let's see how that works. So remember how we shaped memory for simple out of bounds when we allocated many target objects to get new active slab, allocated vulnerable object, filled the active slab with target objects, and then triggered out of bounds to overwrite target. So it might be that you don't want to use that out of bounds bug that you have to directly get control of the kernel, so to exploit the kernel only with that particular primitive. Because out-of-bounds primitives, sometimes they're powerful, but sometimes they can be fairly weak. For example, if you have a single byte out of bounds, it's very hard to corrupt something meaningful inside of the kernel to directly get code execution. So often what people do is they want to upgrade this out-of-bounds primitive to a stronger primitive, and typically people upgrade it to use after free primitive just because use after free is usually way stronger than out-of-bounds in terms of things you can do with the exploit. And let's say we're using such a target object here that contains like a ref counter or some kind of pointer that might get freed or something else at the very beginning of the allocation. Let's say the ref count. So in this case, if we use our out-of-bounds bug to override the ref count of the object, it might be that we will be able to turn this into use after free. For example, we can decrease the ref count, and in this case, the object is going to be freed, the target object can be freed before the kernel gets rid of all the references to it. And this is a case that we're going to discuss. So let's say we shape memory for that simple out-of-bound case, and let's say we chose such a target object that contains a ref counter at the beginning. And let's assume we allocated target object in such a way that the ref counter, the initial ref counter that it has number 2. So we have 2 different references from different parts of the kernel to this target object. So let's use our out-of-bounds primitive to override this reference counter from 2 to 1, just as an example. So we assume that the has the initial ref count of 2, and well, technically we do know that the slab becomes full after shaping. So this, when we executed our out-of-bounds shaping strategy for the simple out-of-bounds bug, we fully filled this slab with target objects, which means it's one of the full slabs right now and it's not tracked by the slope allocator. So let's corrupt our ref counter, increment it from 2 to 1, and then for each target object that we allocated from user space, I assume we have some kind of references to those objects, like a file descriptor or something else, and we're going to close those file descriptors once for each of the target objects to decrement the reference counter from each target object from 2 to 1, at least for those that we initially allocated. But since we corrupted the ref counter for this object that got placed after the vulnerable object, its ref counter was 1. So when we close the file descriptor once, the object got freed, and at this point we have a dangling reference to the slot. And the thing is that this slot is going to be this slab to which the dangling reference belongs. It's going to be one of the per CPU slabs. So remember that during the slab shaping for simple out-of-bounds, we fully filled the slab, which means the slab became a full slab. And by closing the file descriptor, we do now have a free slot within the slab, but it's not the active slab. So it got placed on the per CPU partial list, and let's assume it got placed first there. So the question is now, how do we reclaim that slot on the per CPU partial list in the case when we didn't have the slot on the active slab? So the solution here is very simple. We use slab spraying, and the idea is also very simple. Just allocate more objects. So remember, when we are trying to exploit use after free on the active slab, we just needed to allocate 1 object because we knew that the slot is lost on the lockless free list. But in this case, the slot is buried somewhere deep within the slab allocator free list, so we just need to fill all the slots before it, and this is when we use slab spraying. So the idea itself is similar to the case when we just allocate many objects to plug holes, but I prefer the term spraying when you have some kind of a slot that you're trying to override, trying to target. Like plugging holes, you have many holes, and with this case, you have a particular slot. But the idea is the same. The only question is how many objects do you need to spray, and this depends where exactly your free slot, to which slab exactly it belongs on the lists. So let's assume this case. Let's assume we managed to upgrade our out-of-bounds to use after free, and let's assume we got the first slot on the per CPU partial slab. So how can we fill it? So first we have this new active slab. And the thing is that on this active slab, we might have up to option per slab free slots. Well, technically option per slab -1, but let's assume the case that option per slab slots for active slab. So first we have to fill those slots. So what we do, we start allocating target objects, and this can be different target object. We used one type of target object for out of bounds. Maybe right now, when we have use after free reference, we want to use a different type of target object. But it can be the same one if you want. And so first we have to fill the slots on the active slab, and to do that, we allocate option per slab target objects. And once we allocated option per slab target objects, it might already happen that one of those objects is going to reclaim our slot on the per CPU slab if the active slab was not fully free. So if we only had a few free slots, then once we allocate, like in this case, we had 4 free slots, we allocated 4 objects, and object number 5 is going to be placed here already because this is the next slab that's going to be used But in the worst case, we're going to have 8 free slots within the active slab. So the first ops per slab allocation are going to plug those slots. And the next one is going to be placed inside of the per CPU partial slab. So here, the only difference here is that the free slot with the use after reference, it's buried deep into the list of slabs, so we have to plug all the holes before it, before we can reach it. Otherwise, the idea is similar, just allocate objects to reclaim. Okay, I'm 5 minutes out of my time, but I hope it's okay. I spent 10 more minutes and then we should be done. And let's discuss another approach, how we can shape slab memory for an out-of-bounds for the out-of-bounds case where we have combined allocation and out-of-bounds trigger. So we already discussed how to do it by just kind of like hoping that the slot that follows the vulnerable object is going to be the target object. And in this case, let's see, maybe we can do something else. Now that we know how freeing process works, maybe we can do something better and we can do it without retrying. So I want to explain to you the making holes approach. I don't think this is official name, it's just how I call it. And the idea here is that we're going to create a slab full of target objects, make one hole there, and put our vulnerable object inside of the hole. So this is how it works, how it's supposed to work. First of all, we again allocate many target objects to plug all the holes and get a new active slab partially filled with target objects. Then we allocate even more target objects, ops per slab on top, to make this slab become full. So now we have a slab that's filled with target objects. Now we free one of those target objects. So I assume while we're allocating our target objects, to each target object we have a reference from user space. We don't know the order of the target objects within each slab, but we know that if we go ops per slab allocations back in time, then that allocation will definitely belong to a different slab that we're currently working with. So we just go ops per slab allocations back, free one object, and then we get a slab with a hole. And then the idea here is that we want to reclaim that hole with the vulnerable object, and that immediately going to trigger out of bounds. And this is going to, we're not going to need to retry, because in this case we only have one hole within the slab, everything else is target object. So if our vulnerable object gets placed within the hole, then we will get a target object in the next slot, and then our slab shaping strategy succeeds. The only problem is that placing this vulnerable object within the hole, within this slab that used to be full, is tricky. And the thing is that, again, here we have the case, once we fill the object with the slab with the target object, it became a full slab. And once we make a hole in the slab, it's going to be placed on the per CPU partial list. So if once we get that, we allocate just one vulnerable object, which is immediately going to trigger out of bounds. If we just allocate one vulnerable object, it's not going to be placed into the hole. We already have a different active slab, so it's going to be put in a different active slab. And we could try to allocate multiple vulnerable objects to plug all those holes in the active slab, and eventually this hole is will be used. But the problem is that each time we allocate vulnerable object, it triggers out of bounds. So we don't want to do that, because that will likely end up corrupting some kernel memory. So instead, we need to somehow improve this approach to allow us to make this particular slab to be active again, and only then allocate one vulnerable object. And this is how we're going to do it. So let's start over the whole shaping strategy thing, and let's discuss how to do it to deal with this case. So the first step is going to be the same. We're going to allocate many target objects to plug all the holes and get a new active slab partially filled with target objects. And the number of holes in the slab we don't know, but it can be up to ops per slab holes. The next step is that we're going to reserve many full slabs. So for this approach, instead of just creating one full slab with target objects and making a hole in one slab, we're going to create many of them. And the number of full slabs we're going to create is going to be one bigger than the number of potential holes we might have in the active slab. So we reserve ops per one full slabs. And to do that, we just keep allocating targets. If you allocate ops per slab multiplied by the number of full slabs you want to get target objects, at this point you will get this many full slabs. The next step would be for each of these full slabs, now we have, we know that we have ops per slab plus 1. In this case, it's going to be nine full slabs. What we're going to do, we're going to start going through our list of references in user space to our target objects through the list of file descriptors. So let's assume each time we open a file, a target object gets allocated. So we go through our list of open files, and for each, when we go backwards, and for each obj per slab file descriptors, we close one of them. And this will result in this case, so for each of our full slabs, in each of them we're going to make a single hole. And of course, when we're going to be making the first hole that's going to be made, the slab is going to become the first per CPU slab. That we're going to make another hole, it's going to be also become a per CPU partial slab. But the problem is that for all the caches that you have, the obj per slab plus 1 is going to be bigger than the maximum number of slabs that you might have on the per CPU partial lists. As a result, this per CPU partial list at some point will overflow, and the slabs will spill to the per node slabs. So after you're done dealing with these holes, you're going to have some of the slabs with the hole on the per CPU list, and some of them are going to be on a per node list. And again, the total number of slabs that we have here in this particular case, we're going to have 9 slabs with the hole, and the maximum number of holes we might have on the active slab in this particular case is 8 for the particular picture that I have. So now let's imagine we start allocating objects. So first, objects are going to be allocated from the active slab. Then an object is going to be allocated from the first per CPU slab, at which point this hole is going to be filled and the per CPU slab is going to become full slab and is going to be gone. Then the next per CPU slab is going to be used. Then at some point we're going to run out of these per CPU slabs and we're going to go to the per node list. And that list also have slabs with a hole, so those holes are going to be used next. So let's say the maximum number of holes that we might have in the active slab is obj per slab. Let's first allocate our obj per slab target objects. So as a result, what we're going to have, in this case I use plug objects, but it doesn't matter, target objects work too. For this case I just made it plug objects, so on the picture you can see it better which objects got allocated at this step. So let's allocate obj per slab plug objects. First, those objects were allocated from the active slab. So we had an active slab with 4 free slots, those slots got filled. Then we had some partial slabs, some slabs with a hole on the per CPU list, and those slabs got full. Then maybe we went out to the per node list and some of those slabs got full. But the thing is that at the very end, even in the worst case, we're still going to have at least one slab with a hole, just because we created one full slab more than the total maximum number of holes in the active slab. And at this point, we allocate vulnerable object, and it gets placed within the hole that we have, and we do end up overwriting the target just because we shape memory in such a way that we fill that potentially last slab with the hole at this step with a vulnerable object. So a bit more complicated in this case, we did need to know all the behavior within the slope allocator, we did need to know about all the lists, how to make holes, which is the order of the allocation, and this is the approach that you can use for this combined out-of-bounds approach. So the upside of this approach is that it works even in cases when your out-of-bounds bug might corrupt the free list pointer, if it's like a bigger out-of-bounds, so you end up overwriting free list pointer, which you usually don't want. So this works. This approach also has some disadvantages, and the biggest problem is that it's not very reliable. So first of all, allocating that many full slabs takes time, and it's very likely that you're going to get preempted, especially for caches with very large obj per slab number. And the second thing is that in this approach, we start interacting with the per node list, and this is a global list. And the thing is that other CPUs might interact with that list too, which adds additional source of unreliability. So in certain cases, you might have to do it, but typically slab exploits, they tend to avoid dealing with the per node list just because other CPUs deal with that too, and you don't want that, you don't want any kind of source of unreliability. All right, some notes about double free. So just briefly, typically double free, what people do with the double free, they turn it to use after free. So you free slot once, replace it with some kind of object, free it again. At this point, you have a reference to the object and you trigger use after free. I'm already out of time, so I'm not going to go through that in a lot of detail. So a few final notes. First of all, Sloop is complicated. Whatever I showed here is just a model. It's a simplification. If you want to understand how it actually works, you have to go read the source code. And the two particular starting point I linked here, the starting point for allocation, the starting point for freeing. And hopefully the information on the slides is enough to get you a head start. And then you read the code and it should be understandable. Then some additional links about the slope allocator. The first one is about internals of the slope allocator, and it covers what I covered here, except the slab shaping strategies, and also adds some additional details about slope debug and about Kasan. So I do recommend checking this one out. Then once you're done with figuring out how these basic slab shaping strategies work, you might want to explore cross-cache, and this is the best starting point to explore cross-cache. Sorry, the last article about a good starting point to explore cross-cache. And the part that I didn't cover was about cache merging, the accounting, the different caches, the hardened user copy, and this is the article that you want to check out for that. Finally, some links about those timing side channels that I mentioned. These are 3 different papers. The most modern one is Sloopstick, but the older one you might still want to read them for getting some inspiration or maybe getting some ideas about how to use timing side channels. And yeah, at this, thank you. If you have any questions, I don't know if you have time for questions. What is the format here? There is no moderator, so I guess we have time for questions, but thank you. Sorry? Okay, perfect. Then, yeah, thank you. This is the end of my presentation. If you have any questions, please ask them. Yeah.
I have 2 questions actually.
Okay.
So the first one, in the slab structure in the Keyring cache, you have 2 in fields. You have a CPU partial and you have a CPU partial slab.
Yes.
I'm not sure that I understood correctly the difference between the 2. Can you please explain it again?
Yes. So CPU partial slabs is the actual limit on the number of slabs that you might have on the list. So this is the actual limit. The other number is, I believe this is the limit on the number of object slots that they might want to have on this partial list, but they don't count. I mean, I think this is just some legacy reason. The original code was not limiting the size of the list itself, but the number of free slots that they had on this list. But at some point, they decided it's more efficient to limit the number of actual slabs, so they reworked the code. But since this number was still exposed to user space, they wanted to keep it exposed to user space, the original number of the potential number of, potential limit on the number of free slots on these slabs. So they kept it.
Okay, so the first one is about object. The second one is about the number in the element in the list, right?
Yes, correct.
And the second one, you say that when the slab is full, it's actually put outside of the Keyring cache, outside of the structure. But then where it is stored, because you still need to get the information about it, because if you free something from the full slab, then you will put it back into the Keyring cache.
Yes. So for the slab, we have the slab structure and the backing memory. So the slab structure, it stays there. It's one of the page structures. So there is an array of page structures, or maybe multiple arrays, and this is just an array, and it's always there. And if a particular page structure is a slab, it's just going to have a different layout. So that always stays there. The backing memory, it's allocated from pagealloc, and yeah, if we have a free slot here, there is going to be a link to this free slot. Once we have no free slots, there is no link from the slab structure to this memory anymore. But the thing is that there is, so you might want to explore this vert to slab macro. The way this array of page structures is allocated inside of the kernel, there is basically one-to-one mapping from the array of page structures to the physical pages, to the addresses of physical pages that you have. As a result, if you know the index within the array of page structures, you know the address of the physical memory. If you know the address of the physical memory, you know the index within the array. It's slightly more complicated because you can have multiple arrays, but the idea is still the same. If you know the address, you can get the address of such slab accordingly. So the code, what it's going to do once you get a pointer to a certain object, is just going to use that vert to slab macro to get the address of the corresponding struct page. And that macro just calculates the address within the array of page structures based on the address of the page.
Thank you.
Yeah.
Thank you for the great presentation. Just out of curiosity, recent additions, I think it's in 6.11 kernel, we do have the option for allocating or for using different caches, basically one per subsystem, for example.
Yeah.
I believe there's also something similar provided by GR Security that works very similar, let's say. From my understanding, I mean, I understand how it protects against these kinds of attacks, but it doesn't completely solve the problem, correct? It basically reduces the attack vector to that subsystem, meaning that the attacker will have to be able to control both sides, allocating and freeing from the same subsystems, but the end effect is fatal.
So, yeah, I mean, I think you're referring to the patch set by case. That's essentially, this is not something I discussed during the presentation, because in the presentation we focused on a specific cache. So we assume we have a cache, we assume we have ways to allocate objects from the cache, and we didn't discuss cache interactions. But the thing is that within the kernel, yes, you might have those common kmalloc caches, for example, and different parts of the kernel, if they use the same cache, the objects allocated from the different parts of the kernel, are going to end up in the same cache. And that patch set prevents that type of thing of happening. So like the latest patch set that's still being discussed is one based on the code location inside of the kernel code, even though the code, like the call that you have to the allocation function, it's still kmalloc, it's supposed to be using kmalloc cache, but at this point, for each code location, you have your basically standalone cache, a separate cache, and it just uses allocations from that cache. But yeah, that does not prevent the problem. Well, it prevents a part of the problem. It makes it way harder to choose, for example, target objects for exploitation. So in the case that I discussed here, let's assume we can have vulnerable object coming from one kernel subsystem and target object can be coming from completely different kernel subsystem. This is what happens typically right now without this patch that case has. But once you have that patch, if you have a certain vulnerable object, that means you will have to base your exploit on corrupting the same type of an object. So you're going to have to use vulnerable object or object of the same type as your target object. It still does not solve the problem fully, because you can still corrupt objects of the same type, and it might give you some kind of a better primitive that you will use for some other things. But it definitely makes it harder. Yeah. Well, I mean, I don't know. So this thing that case has, the last one, the one we just discussed, it's fairly exciting. I don't know if distributions will actually enable it, because as far as I understand, it results in big fragmentation. But we'll see. This is one of the things that is cool. Another thing is the Slab virtual thing by Jan Horn and some other people from Google. So this is the thing that prevents cross-cache attacks. This is something I didn't talk about, but essentially, what they do is they try to limit the, basically for each cache, so imagine you have a cache, and you have slabs that are allocated for that cache. And those slabs contain objects of a certain type. And what they want to do, they want to avoid cases when you have a reference, when you have some kind of a cross-slab interaction. For example, if a cross-cache attacks, the way it works is, let's say you have a use after free reference to a object slot within the slab. They take the whole slab, they free everything else in there, they free it back to page alloc, and they allocate it as a slab for a different cache. And as a result, you might have a reference, use after free reference to certain memory, which was originally a slab for a cache type A, and at the end you have a reference to a cache type B, which allows you to do a lot of fun things. And Slab virtual prevents that. This is one of the things that makes it fairly interesting. It's also not bulletproof, because at the moment you're doing cross-cache, you can do a cross-allocator, how I call it, cross-allocator attack. So instead of corrupting once you freed memory back to page alloc, instead of allocating this memory as a memory of another cache, you can just allocate it as page tables. It's just a simple page allocation, and you can corrupt page tables, which is a very flexible approach. So something else needs to be done about that. But for cross-cache attacks specifically, Slab virtual is quite fun. And otherwise, yeah, we have MT, at least we have it, kind of have it on ARM. Well, we do have it on ARM. The question is, we don't yet have it in the Android kernel. There is a debug implementation that's not enabled by default, but MT will certainly make it very interesting for a lot of cases for this type of memory corruptions primitive. So MT is memory tagging for those who don't know. This is another type of a mitigation. Essentially, the MT allows tagging different slots of memory with different tags and different pointers with different tags. And then the memory can only be accessed through a particular pointer if the tag on the memory matches the tag on the pointer. So if you manage to somehow make the pointer point to a different part of memory, the tags are not going to match, and you're not going to be able to dereference the pointer. All right, thank you. Well, I mean, you can ask still.